Take a single strand of your hair and lay it flat on the table. Now look at it. At approximately 70,000 nanometers, this is one of the smallest things you can actually perceive with your own eyes. And even then, it's just barely visible on a good day. And if you're blonde, well, good luck. Now what if I told you that a single quantum particle, the proton, is about 700,000 times smaller than that strand of hair? To put it in perspective, let's increase the size of the proton to be as big as a grain of sand. At that scale, how big do you think your hair would be? An entire house? A block of flats? Wrong. Picture Manhattan. The full island. The skyline you've seen in 1,000 films. The chaos of Times Square. The quiet end of Central Park. 1.6 million people. 400 kilometers of subway tunnels running underneath them. Bridges. Tunnels, skyscrapers so tall they have their own weather at the top. All of that, every last inch of it, twice. That's how big a single strand of your hair would be. Your intuition was built for the world you can see, the world of falling objects and moving cars and faces that you can read across a room. It was never designed for this. It has no frame of reference for this. And yet, down at that scale, in the world that sits completely outside the reach of human perception, the rules are different, not a little different, fundamentally, impossibly different. But unfortunately for us, those rules don't stay down there. They shape everything that comes up here. The atoms in your body, the electricity in your brain, the light hitting your eyes right now. Everything you are and everything you can see is built on top of a foundation that behaves in ways your intuition will never naturally accept. For the next few hours, we will be exploring the most disturbing quantum theories that break reality, each idea scarier than the last. This is not a series of answers, it is a map of the edges of human intuition and our greatest scientific research, where physics ends and something far stranger begins. There is a quiet assumption that sits beneath almost everything that we believe about the world. It is so deeply embedded in our thinking that we rarely notice it, and yet it shapes how we interpret every object, every event, everything that we experience. The assumption is simple. Things exist independently, and they influence one another through space in very predictable ways. A cup sits on a table whether you're looking at it or not. A signal travels from one point to another, never faster than the speed of light. Objects are separate and distance is real and tangible. For centuries, this assumption wasn't just philosophy, it was physics. Classical physics, as we now call it, built on the work of Isaac Newton, described a universe that behaved like a vast but precise machine. Every object had a definite position, a definite velocity, and a future that could, at least in principle, be predicted if you had enough information about the present. Reality was stable, it was local, and it was understandable. Then quantum mechanics arrived and dismantled all of it. Our entire assumption of reality was completely broken, and this new version of reality terrified even the most brilliant of minds. This is the theory of quantum entanglement. So at first, the cracks appeared small. Tiny particles like electrons and photons refused to behave like solid objects. They didn't follow clear paths or settle into definite states. Instead, they existed in something far more unstable, a condition known as superposition. Before being measured, a particle doesn't have a single fixed property. It exists as a range of possibilities simultaneously. What this means is that reality, at its most fundamental level, is not composed of solid things, but of unresolved potentials, So this is really where intuition begins to fail us. In our everyday life, uncertainty is usually a reflection of incomplete knowledge. You flip a coin and you cover it before looking at the result. The result is still already determined, you just don't know it yet. But with quantum mechanics, the coin exists in a state of both heads and tails until you measure it. This alone is strange, but it's not what breaks reality. This is only the beginning, to be frank. The real reality breaking begins when two of these quantum particles interact with each other. Under certain conditions, when particles come into close contact or are created together, they sort of merge. Instead of having separate states, they become part of a single shared system. In quantum mechanics, this system is described by a joint wave function. It's a mathematical object that contains all possible outcomes for both particles at once. At this point, something subtle but very profound happens. The particles are no longer independent entities. They're different expressions of the same underlying system, and this phenomena is what we call quantum entanglement. To make sense of this, we have to lean on some analogies. One of the most common analogies is the idea of a pair of gloves. If you were to place one glove in a box and send it across the world while keeping the other glove with you, opening your box immediately tells you what is in the other box. If you see a left glove, the distant box must contain the right glove. And there's nothing mysterious about this. The outcome was determined from the beginning. But entanglement doesn't behave like gloves. In the quantum case, neither particle has a predetermined state while traveling, and there's no hidden label attached to each one. Before measurement, both particles exist in superposition. They are not secretly decided, they are genuinely unresolved. And yet, when you measure one, the other responds instantly. If one particle is observed to have a specific property, such as spin up, the other will immediately take the corresponding opposite state, even if it is separated by vast distances, and there's no delay to this. It's not a signal traveling from one particle to another through space. The correlation appears to happen with no time passing at all. So this is where the structure of reality begins to fracture. Because this behavior violates something deeply embedded in classical thinking, local realism. The idea that objects have definite properties and that any influence between them must travel through space over time. Entanglement rejects both parts of that idea simultaneously. It tells us that particles do not have definite properties until they're measured. And it tells us that the outcome of one measurement can be linked to another across any distance, without any observable transmission of information between. Albert Einstein found this deeply troubling. So much so, in fact, that he referred to it as spooky action at a distance. Not as a poetic description, but as a frank criticism. To him, it signaled that quantum mechanics was incomplete, that something essential was missing from the theory. If entanglement were true in the way quantum mechanics described, then reality itself could not be built from independent parts. It would mean that separation, the very concept of distance, might not be fundamental to reality. Two objects could behave as one system, regardless of how far apart they appeared. And this introduces a contradiction that is very difficult to resolve. Because everything about our perception as humans is built on separation. You experience the world as divided into objects. Each object has boundaries, each existing in its own location. You rely on the assumption that what happens here is independent of what happens elsewhere, unless something physically connects them. Entanglement suggests that this assumption is not just incomplete, but also fundamentally wrong. It implies that at the deepest level, reality is not made up of things, but of relationships. This shift is subtle, but it carries significant consequences. If two particles can form a single system across space, then space itself begins to lose its meaning as a separator of objects. From this perspective, the universe doesn't consist of isolated objects interacting across empty space. It consists of interconnected systems that only appear separate when observed at a certain scale. And this is where the discomfort deepens, because it suggests that the world that we experience, the stable, predictable, object-based reality, is not a foundation of existence. It's a simplified version, a Coles Notes, an emergent layer that hides the deeper structure beneath it. And that is a structure where independence is an illusion, where properties do not exist until they're measured, and where 2 points in space can behave as if they are not separate at all. So at this stage, it is tempting to interpret entanglement as a kind of hidden communication, an invisible signal passing between particles that travels faster than light. But this interpretation quickly collapses under close examination. Because while, yes, the correlation is instantaneous, it can't be controlled. When you measure a particle, the outcome is completely random. You can't choose whether the particle is up or down. And because you can't control the result, you can't use it to send information from one point to another. And this creates a strange limitation. The universe allows for perfect correlation across distance, but denies any ability to use that correlation for communication. It connects outcomes, but not intentions. The result being a system that appears to violate the very structure of space while still preserving the rules of causality. This balance is not intuitive. It doesn't resemble anything in everyday experience, so it feels incomplete, as if there should be an underlying mechanism that explains how that connection works. For decades, physicists believed there must be. Einstein proposed that hidden variables, unseen instructions embedded within the particles, determined their outcomes in advance. In this view, the randomness of quantum mechanics was only apparent. Particles already knew what they would become when they were measured. And this theory would restore order to the system. It would preserve locality. It would allow reality to remain structured in a familiar and comforting way. But it also comes with a cost. It required accepting that the universe contained deeper layers of information that were fundamentally inaccessible, hidden beneath the observable world, and for a time, this seemed like a reasonable compromise. Well, until it was finally tested. What followed would not just challenge Einstein's intuition, it would destroy it entirely. There was a period in physics where the strangeness of quantum mechanics could still be dismissed as temporary confusion. It was assumed that with enough refinement, the theory would eventually reconcile itself with common sense, that the universe at its core would still obey the principles that had guided science for centuries. And those principles wouldn't be arbitrary. They formed what is known as local realism. Realism is the belief that physical properties exist independently of observation. A particle has a position, whether you are measuring it or not. A system has a state even when no one can see it. Reality is objective, stable, and external. Locality is the constraint that nothing can influence anything faster than the speed of light. Causes propagate through space over time. No effect can appear instantaneously at a distant location. Together, these ideas form a coherent picture of the world. Objects exist, and they interact through signals. Space separates them, and time governs their influence. Well, quantum mechanics threatens all of that. Einstein understood this immediately. His discomfort with entanglement wasn't about mathematical elegance or philosophical preference. It was about preserving the structure of reality itself. If quantum mechanics were correct as it stood, then either realism or locality, or even both, had to be abandoned wholesale. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, formalized this concern in what became known as the EPR paper. The argument was very carefully constructed. It did not attempt to disprove quantum mechanics outright. Instead, it aimed to show that the theory couldn't be completed, that there must be an additional variable hidden beneath the surface that restored a definite reality to the systems that we observe. And you know what? The logic was straightforward. If two entangled particles are separated by a large distance, and measuring one instantly determines the state of the other, then one of two things must be true. Either the measurement sends a signal faster than light, violating locality, or the second particle already had that state before the measurement took place, preserving locality but requiring hidden variables. Einstein rejected the first option entirely. Anything being faster than light would contradict his most famous and successful theory of relativity, so he concluded that the second option must be correct. The particles must carry predetermined instructions that dictate their outcomes. These hidden variables would explain the correlations without requiring any spooky interaction. They would restore realism and maintain the integrity of space, and for decades this remained an unresolved debate. Until Niels Bohr, one of the founding figures of quantum mechanics, argued against Einstein's position. He claimed that the act of measurement is not a passive observation, but an active process that defines the properties of the system. According to Bohr, it is meaningless to talk about a particle having a definite state before it is measured. The question itself is just invalid. And this wasn't a disagreement about data, it was a disagreement about what the data meant. And for a long time, there was really no way to decide between them. You picked one side or the other. But the turning point came in 1964, when an Irish physicist named John Bell found a way to translate this philosophical conflict into mathematics. Bell's insight was deceptively simple. If hidden variables exist, they cannot produce arbitrary correlations. They are constrained by certain statistical limits. There is a maximum strength to the correlations that any local hidden variable theory can produce. This limit became known as Bell's inequality. Quantum mechanics, however, predicted something different. It suggested that entangled particles could exceed this limit, that their correlations would be stronger than any pre-programmed set of instructions could allow, and this created a very clear test. If experiments obeyed Bell's inequality, then Einstein's intuition was correct, and hidden variables existed. If they violated it, then local realism, the foundation of classical thinking, would have to be abandoned. For the first time, the question was no longer philosophical, it was empirical. In the 1970s, the first experiments were conducted. They were technically difficult, requiring precise control over entangled particles and their measurements, but the results were consistent. Bell's inequality was violated, and it has been violated in every increasingly refined experiment since. This result carries a very specific and very clear implication. It doesn't simply suggest that quantum mechanics is correct. It eliminates an entire class of possible explanations. It proves that local hidden variables, the last refuge of classical intuition, do not exist. The particles aren't following pre-written instructions. They're not secretly determined in advance. And yet, their outcomes remain perfectly correlated. And this leaves only one conclusion. The universe is non-local. Non-locality doesn't mean that information travels faster than light in any usable way. It means that the concept of independent localized objects breaks down at the quantum level. Entangled particles are not separate entities exchanging signals. They are components of a single system, regardless of distance. From this perspective, asking how one particle affects the other, it's the wrong question. There's no influence traveling between them because they aren't two independent things to begin with. There's only one system expressing itself in two locations. And yes, this is difficult to accept because it conflicts with how perception is structured. Human experience is built on the idea that space divides objects, that distance creates independence. Well, non-locality suggests that this division is not fundamental. It suggests that separation is, in some sense, an emergent feature, not a basic one. And this creates a deeper tension. Because if space does not fundamentally separate things, then what does it mean for anything to be somewhere? What does location represent if the underlying system is not confined by it? And these questions do not have intuitive answers. They force a shift away from thinking in terms of objects and towards thinking in terms of relationships. In classical physics, relationships are secondary. The object exists first, and relationships describe how they interact. In quantum mechanics, relationships come first. The system exists as a whole, and what we call objects are derived from how the system is observed. This inversion is subtle, but it changes everything. It means that knowledge of the whole doesn't translate into knowledge of the parts. As Leonard Susskind points out, you can know everything about an entangled system and still know nothing about its individual components. And it introduces a form of ignorance that can't be resolved. No matter how precise your instruments become, the individual particle remains undefined until it's measured. In quantum mechanics, reality is partially constructed through interaction. The act of measurement doesn't reveal a pre-existing state, it brings a state into existence. And once you accept this, you start to see its implications way beyond physics. Because it suggests that what we call reality is not a fixed structure, but a process. A continuous unfolding of interactions that define properties in the moment that they're observed. This doesn't mean that consciousness creates reality, as it is often misinterpreted. Measurement in physics doesn't require a human observer. It can be any interaction, any exchange of energy or information between systems. But it does mean that the idea of a fully independent, observer-free reality becomes difficult to maintain. Now the question is, how does a universe built on probabilities, non-local connections, and undefined states give rise to solid objects, stable identities, and predictable cause and effect relationships? The answer lies in a process called decoherence. At its core, decoherence can simply be expressed as the dilution of quantum entanglement. It describes what happens when a delicate quantum system interacts with its environment. Instead of remaining isolated, the system becomes entangled with countless surrounding particles, air molecules, thermal radiation, and electromagnetic noise. Each interaction spreads the quantum information outward, distributing it across a vast number of degrees of freedom. What once was a clean, isolated superposition becomes entangled with the environment in such a complex way that it can no longer be observed as a coherent whole. The system doesn't lose its quantum nature, it just becomes too entangled to track. Think of it like trying to hear your friend whisper in a crowded room. The original signal is still there, but it's completely overwhelmed by the background noise. This is exactly what happens to quantum systems in the real world. Entanglement, rather than being rare, is actually ubiquitous. Everything is constantly interacting, constantly exchanging information, constantly becoming entangled with everything else. But because this entanglement spreads so quickly and so widely, it loses the sharp correlations that make quantum effects noticeable. At large scales, the chaotic web of quantum interactions averages out into stable, classical behavior. Objects do appear to have definite positions, systems behave independently from one another, and cause and effect seems local and, thankfully, continuous. This is why physicists are able to observe entanglement in controlled laboratory environments. By isolating systems from environmental noise, they temporarily prevent decoherence from washing out the correlations. But outside of these conditions, the environment dominates. This means that the classical world is not a separate layer of reality, it is a byproduct of entanglement spreading beyond our ability to observe it. And this reframes how we understand separation. Because if everything is constantly interacting, constantly becoming entangled, then the boundaries between objects are not fundamental divisions, they're approximations. They're useful distinctions that emerge from complexity, but not from the underlying structure. At the quantum level, the universe behaves less like a collection of independent parts and more like a continuous system with shifting correlations. There's a tendency to treat quantum entanglement as a technical problem, something confined to laboratories, equations, and abstract models of particles that behave in ways disconnected from human experience. But this separation is misleading, because the real disturbance of entanglement is not what it does to physics, it's what it does to the human experience. For most of human history, reality has been treated as something stable, external, and ultimately understandable. Even when phenomena appeared complex, the assumption remained that beneath that complexity was a coherent structure governed by very clear and definite rules. The goal of science was to uncover those rules and translate them into a form the human mind could grasp. Quantum mechanics disrupts that expectation by undermining the framework that makes reality feel interpretable. It reveals that the categories that we rely on, that's object, location, state, cause, all of these things are not fundamental to reality. They are approximations that emerge under very specific conditions. Entanglement makes this especially difficult to ignore, because it introduces a form of connection that cannot be reduced to interaction. It shows that systems can be fully defined as a whole while remaining undefined in their parts. That knowledge doesn't necessarily decompose into smaller, more manageable pieces. This contradicts a basic assumption of understanding itself, the idea that to understand something is to break it down. In classical thinking, reduction works. Complex systems can be analyzed by studying their components. If you understand the parts, you understand the whole. But entanglement reverses the logic. The whole contains information that the parts don't, which means that certain forms of knowledge are inherently non-reducible. They can't be simplified without losing what makes them accurate. This creates a subtle psychological tension, because the human mind is structured to seek clarity through division. It isolates variables, defines boundaries, and builds explanations by separating systems into discrete elements. Entanglement resists this process. It presents a structure where separation obscures rather than clarifies. And this is where the discomfort begins to extend beyond physics, because it suggests that the limitations are not only in the theory, but in the way the mind approaches reality. That there are aspects of the universe that cannot be made fully intuitive because they are incompatible with the frameworks we use to understand them. The brain evolved to handle environments where objects are large, interactions are local, and outcomes are relatively stable. It developed shortcuts that prioritize efficiency over accuracy, and these shortcuts work, for the most part, because at the scale of everyday life, they produce reliable results. But quantum mechanics operates outside of that domain. It exposes a layer of reality where those shortcuts fail us, where the assumptions they rely on don't apply, where intuition, instead of guiding understanding, actively interferes with our understanding. This is why even highly trained physicists often describe quantum mechanics in terms of what is not. It's not classical, it's not local, it's not deterministic. That language reflects a kind of boundary where the goal isn't to make the system feel natural, but it's to describe it accurately despite its resistance to intuition. And this creates a shift in how knowledge is experienced. Understanding becomes less about forming a clear mental picture and more about accepting a structure that cannot be fully visualized. The equations remain consistent, the predictions remain reliable, but the interpretation is incomplete in a cognitive sense. This is where the idea of reality begins to change, not necessarily in its behavior, but in how it can be known to us. Because entanglement suggests that there may not be a single observer-independent description of the world that is both complete and intuitive. That different frameworks may capture different aspects of the same underlying system without fully overlapping. That any description of reality is filtered through the tools used to construct it, whether those tools are mathematical formalisms or cognitive models. All of this leads to a quieter implication, that certainty, as it is commonly understood, may not be achievable at the deepest level because reality does not conform to the structures that make certainty possible. In classical physics, certainty comes from determinism and locality. If you know the initial conditions and the laws governing the system, you can predict its future. In quantum mechanics, even complete knowledge of the system doesn't yield definite outcomes for individual events. You can know everything about the wave function and still only be able to predict probabilities. This doesn't arise from ignorance, it's a feature of the system, and it forces us to redefine what it means to truly know something. Knowledge becomes statistical rather than absolute, predictive rather than definitive. Instead of revealing a fixed structure, explanation becomes a way of navigating this uncertainty. It provides constraints, patterns, and relationships, but not final answers in the classical sense. Thankfully, though, this still does have a stabilizing effect, because while the foundation of reality may be uncertain, the emergent layer remains consistent. At the level of everyday experience, probabilities average out. Objects behave predictably. Systems follow patterns that can be relied upon. Yes, the instability is still there, but it's contained. This is why quantum mechanics doesn't disrupt daily life. It just doesn't need to. The classical world isn't false, it's just incomplete. It is a layer of approximation that works within a certain range of conditions, and within that range, it does remain valid. But entanglement reveals that this layer is not the foundation of the building. It's built on something else. The deeper you go into the structure of reality, the less it resembles the version that you experience. The more accurate the description becomes, the less intuitive it feels. And understanding that transition requires letting go of a specific expectation of the world. The expectation that reality should make sense in human terms. Because the history of physics has gradually moved in a very different direction. From a world that behaves like a machine, to a world that behaves like a system of probabilities, to a world that may be defined by relationships rather than objects. Each step along this process has reduced the role of our intuition. Each step has required accepting that the universe is not obligated to match the way it is perceived. Entanglement is not the final step in that process, but it is one of the clearest. Entanglement shows that separation isn't absolute, that properties are not fixed, that space may in fact be emergent, and that knowledge itself has limits that are not due to lack of information, but due to the structure of reality itself. The result is a shift in what understanding means to us. It becomes less about building a coherent picture and more about recognizing where coherence breaks down and what we can do about it. It's less about simplifying reality and more about accurately describing its complexity. And in that shift from one to the other, something does finally become clearer. The problem isn't that reality is broken. It's that the model that we inherited was never built to describe it at this level. Quantum entanglement doesn't destroy our reality, it just reveals that what we call reality was always just the surface. So the universe is not made of separate things. That isn't a metaphor, it's not a poetic way of saying that we are all connected in some vague spiritual sense. It is a measurable, tested, repeatedly confirmed feature of physical reality. Particles that have interacted share a state. Measure one, and the other resolves instantly, regardless of the distance between them. Einstein spent the last decades of his life insisting that this was wrong, but the experiments proved otherwise. But notice what entanglement doesn't yet tell us. It tells us that particles are connected. It doesn't tell us what particles actually are before that connection is measured, before the experiment runs, before anyone looks. And here's where that strangeness gets worse, because the answer that quantum mechanics gives us to that question isn't, well, we don't know yet. It isn't, there is information that is hidden that we haven't found yet. The answer is more troubling than even that. Toss your phone up in the air. Newton says it's going to come down. Safe, predictable, normal. Classical physics is the part of reality that we turn to for clarity. If you follow the math, there's usually a definitive answer. Now, imagine if sometimes the phone doesn't come down, or sometimes it doesn't stay up, or sometimes it moves to the left, and it just randomly decides to go wherever it wants. That's the strange reality of quantum mechanics. But quantum mechanics is awesome, by the way, because it doesn't simply break the rules. It completely shatters our understanding of reality itself. Nobel laureate Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." Even Einstein himself got theological about the concept, saying, and I quote, "God does not play dice with the universe." But unlike philosophical paradoxes, quantum paradoxes are actually baked into the universe, and each one is more terrifying than the last. Now, among these strange ideas, there's one concept that you can never shake off when discussing quantum physics, and that's the concept of superposition. It's the idea that something can exist in multiple states at once up until it's observed. It sounds fictional because in our everyday world that is literally impossible. Superposition once gave physicists sleepless nights until Erwin Schrödinger broke it down with a famous measurement problem. You may be more familiar with it under the name Schrödinger's cat. The quantum world deals with tiny particles like electrons, for example. Because of superposition, an electron can be in spin up and spin down at the same time until you look at it, and that is the coolest thing. And then you can suddenly know for sure what position it was. What Schrödinger did with superposition was expose just how ridiculous sounding it truly is. So we'll use his example. Imagine a sealed box with a cat inside of it, and along with the cat there's also a tiny radioactive atom. If the atom decays, a poison is released. If the atom doesn't decay, nothing happens. Whether or not this atom decays is a quantum event. So here's the paradox. Quantum mechanics states the atom in question is both decayed and not decayed. Considering the fact that the atom contains a poison, its state determines whether or not the cat is alive. But that's the heart of the problem. Before you open the box, it feels like the cat is both alive and not alive. It's the sort of idea that tears a hole through reality in sci-fi stories. Now, ironically enough, this was Schrödinger's point. He was trying to show us something with this measurement problem. Yes, it's an interesting thought experiment to think of the cat in both states, but his core argument was that quantum rules do not make any sense when applied to everyday objects. Schrödinger's cat is essentially a mockery of naive interpretations of the quantum realm. And when you think of the quantum world, It's crucial to avoid fitting it into a box of conventional expectations and logic. True understanding comes from embracing quantum mechanics as its own thing, its own kind of weird. Now, Schrödinger's cat is just the warm-up. It's pointing to an even stranger outcome. If reality only becomes definite from our observation, then what is making the decision for the definite things that we see? Is it us? Is it some measuring device? Or is there something pulling the strings that we can't perceive? Now, Einstein noticed this problem and he did search for answers. Here's what he found. 2 quantum particles created in a single shared quantum state. For ease, let's call them particle A and particle B. Now, the pair are entangled together in a way that links their properties. Generally, quantum particles tend to have distinct properties like mass, spin, and charge. These 2 particles are then allowed to fly light years apart, so much that they basically don't even exist within the same area in space. To make it simpler, imagine 2 coins with the ability to act inversely of each other. So you flip one coin and it lands on heads. Well, by that logic, the other must be tails. And no matter how far apart those coins get, say I have one of the coins with me in Toronto, while the other is in Australia, then my coin flip will inevitably correlate with the coin flip in Australia and vice versa. Now, these quantum particles are linked, even when they are light years apart. So, if particle A is measured to have spin up, then particle B must instantly have spin down with the same applying and vice versa. Now, we're building on this. Remember what we said about superposition and observation. Before we measure particle A, it's in superposition, so we don't know for sure if it's spinning up or down. But if we observe it to have a spin up, we can conclude that particle B has spin down. And this conclusion is thanks to the way that their properties are linked. But Einstein, and I adore this, called this spooky action at a distance. For a scientist at his level, there were certain foundational truths driving the completion of a theory. The 2 classical principles he held on to were locality and reality. Locality means that an object can only be influenced by its immediate surroundings. Put simply, nothing can travel faster than the speed of light. Next is reality, where the physical properties of an object exist when they are not being observed. So, why did all of this bother someone who could arguably be called the smartest man to ever live? Well, let's look at it this way. If I were measuring particle A in this room, and my cousin Steve in Australia is measuring particle B, we'd know each other's coin states based on the correlations that our particles have. So even if Steve was light years away in Andromeda, once I observe heads on particle A here on Earth, particle B all the way out there is guaranteed to have tails. And that's how it works for the pair's particular entangled setup. This spooky action implies that the measurement that I made instantly influenced particle B no matter the distance. And that was problematic to Einstein's principle on locality because it's unquestionable. Particle A correlated with particle B instantly, even while they were light years apart. To understand it better, 1 light year is about 9 trillion kilometers. This interaction is unfathomable to a rational mind. Currently, this level of correlation is not usable for communication, so nobody can actually send information faster than light. Yet, the weirdness endures. 3 physicists, Einstein, Podolsky, and Rosen, drew a conclusion to the problem. Essentially, they believed the spooky action to be impossible, arguing that the only way to avoid it is if the particles already had their definitive spin values determined from the beginning. These predetermined values were called local hidden variables, but the 3 couldn't actually prove the existence of these local hidden variables. They weren't claiming to know what these variables were, only that there was a gap in the logic. And that gap is terrifying. A quantum paradox that's essentially sealed away by science's greatest minds. If you were to explain Einstein's point of view to a 6th grader, it almost feels like Einstein closed the gates of an unknown realm. Without a concrete answer, engaging with it risked something far greater than what Einstein was ready to accept. So, for nearly 30 years, Einstein, Podolsky, and Rosen's point of view remained a philosophical debate dubbed the EPR paradox. Enter John Bell, the man that transformed this paradox into a mathematical inequality called Bell's theorem. Bell realized a distinction between the predictions made by quantum mechanics and the predictions of any theory that satisfied Einstein's principles of locality and reality. The main distinction was quantitative. So he created a complex set of measurements to perform on particle A and particle B, turning Einstein's complaint into a testable equation, like a mathematically intense game of truth or dare. And here's what it boils down to. If Einstein's local hidden variables were correct, the measurement correlations between both particles could not exceed a certain mathematical limit, and he called this the Bell inequality. On the other hand, if quantum mechanics was correct, the correlations would exceed this limit. The conclusion proved that Einstein was looking at it the wrong way. Now, that doesn't mean he was completely incorrect. It's just that the quantum world is non-local. So it's like he was applying basketball rules to a game of soccer. In the literal sense, quantum mechanics predicts these strong correlations as an accurate description of the universe. But for us to truly understand it, we must sacrifice those ideas of locality and reality. That leaves the spooky action as a very real thing. And now, interestingly enough, even though the particles are correlated, there's really nothing that shows us how this can transmit useful information faster than light. The EPR problem and Bell's theorem further drive home the idea that the quantum world doesn't play by our universe's rules, but they do both seem to draw on a final observation. Right now, it might feel like you understand quantum mechanics a tiny bit better. The concept is a lot like buying a Labubu doll. You never know which one you're going to get in each mystery box, that's what I'm trying to say here. But you can still measure probabilities. But what if I told you that sometimes, depending on the Labubu you get, you can retroactively change the past? To really grasp what I'm saying, let's take a look at a famous piece of foundational physics, the double slit experiment. Let's get nerdy with this. So imagine a wall with 2 parallel cracks in it. Let's say you have a gun that shoots out single photons of light. Photons are they're not a wave, they're not a particle, but we'll call them particles of light for ease. When you begin firing the tiny particles at this wall, you expect to see 2 distinct lines shining brightly behind the cracks. But that doesn't happen. Instead, you find a shimmering interference pattern with many bright and dim stripes. This is the signature appearance of a wave, meaning that each particle isn't just taking one path. Instead, it's going through both slits at once, which a particle can't do. And as those possibilities interfere with each other, a pattern is created. That's when you decide to put a detector at the slits. Now, this detector measures which path the photon bullets took. So you fire up the experiment again, and you fire that gun. But this time around, something strange happens. The interference pattern at the back of the slit vanishes. Instead, the particles behave like you would conventionally expect, creating 2 distinct bands of light directly behind the cracks. I love that. This experiment establishes a rule with quantum mechanics, and that rule is, when observing, you can either see the wave behavior and the interference, or you can get the path information, but never both at the same time. It's like getting the information causes a collapse in the wave function. The particle feels aware of an observer. I just want to repeat that for how mind-boggling it is. The particle knows you are looking at it, so its behavior changes from the stage fright. It's wild. Now, I want to pause it here. It's not literal awareness, though. It's not looking at you and having thoughts like we would. The wave-like possibilities actually collapse into a definitive outcome. It's like the act of checking freezes it into a single choice. Now, looking changes reality in the present, but you have to wonder, has anyone ever tried to look after the fact? Like you'll come to learn along the way. Someone has in fact asked most of these burning questions in quantum physics. In this case, we have something called the quantum eraser paradox. Instead of firing single photons, what if an advanced setup generated pairs of entangled photons, just like we observed in the earlier EPR problem? Let's just call them photon A and photon B. Photon A plays the role of the signal photon. It's the brave mercenary that we're sending towards those double slits. Meanwhile, photon B is the idler photon. This is the one we use to get the answer on which path photon A actually took. Now, we have a special device at the slits to give photon A a barcode, depending on which slit it went through. Because photon A got the barcode, photon B also inherits knowledge of this barcode thanks to the pair's entanglement. Then photon B flies off to a distant area for detection, carrying the secret of which path photon A took. So, here's one of the possible results. Because of the information available to photon B, photon A acts like a particle and the screen shows two distinct bands. In other words, no interference. This result is the same as the double slit experiment. The interference pattern is destroyed by observation. Now, another possibility is what I would like to call the eraser. So, let's take a look back at photon B after it flew off into the distance. As an experiment, it's sent through a quantum eraser that destroys any possibility of ever knowing which slit photon A took. If you're not sure why anyone would want to do that or care, stick with me, we'll get to it. Here's where things get interesting. When taking another look at photon A after scrambling photon B, something strange happens. Its data is correlated with what is erased on photon B. In other words, an interference pattern magically reappears. It's like it undoes the result of being observed. Because photon's B information got scrambled, photon A starts to behave like a wave. And if you're not going right now, let's run it back again for some more clarity. Photon A hits the screen and does the conventional double slit observation. We record the journey, get the data, and we know with certainty that it ended its journey as a particle. Now, erasing the barcode doesn't rewrite photon A's past. It only reshuffles the data. Yet, from the way it appears, it's as though photon A has already recorded past changes because of what is happening with photon B. It's like watching a detective show. When the big reveal happens, you realize that the clues that you ignored earlier suddenly change how you interpreted the case. Quantum mechanics can behave in ways that are eerily similar. So, what does this tell us about time? Is it the linear journey that we believe in? From the quantum eraser, it feels like changing the present can influence the past, which is creepy but also very fun to think about. And it's not entirely far-fetched. Today, episodes of shows that aired decades ago are edited quietly to fit a new vision. A politically incorrect joke is quietly phased out. And sure, that fits with the times, but if we jump at every opportunity to cover up a messy past, what kind of future are we shaping? Maybe reality and fiction don't truly exist within distinct lines. Most times, we doubt the realities observed by others, like when your friend barges into your college dorm room claiming that a test was graded. To you, it might sound unbelievable, especially when the grades are out before the scheduled time. Meanwhile, if your friend is coming from the professor's office, they've just observed a different reality. Now, both are technically true, yet there's one objective truth in play. The quantum world has something that invokes the same sentiment, but this time things are so fantastically, fascinatingly paradoxical. This time, let's bring back my cousin Steve from Australia. So Steve gets into a sealed lab and performs an experiment to measure the spin of a particle. Remember, that in quantum mechanics, particles are usually in superposition. So prior to measurement, it seems like a particle is up and down at the same time. Steve performs the measurement and he finds the particle is up. Acknowledging this, he writes it down in a note. Meanwhile, I'm outside the lab. While Steve carries out his experiment with the quantum particle, there's something that I, where I am, can't seem to grasp. You see, Steve, the particle, the measuring device he's using, and the notebook are now part of a single quantum state. Furthermore, from my point of view, the sealed lab and everything within is in a state of superposition. This state will persist until I open the door to the lab and perform my own observation. So where exactly does this collapse into superposition actually happen? More importantly, why does it happen? I know that Steve must have recorded a result, but the superposition still remains as long as I haven't made my measurement. Fundamentally, we tend to assume that there's a definite boundary between the microscopic quantum world and our conventional classical world, yet they exist together. This isn't just philosophy. The 2025 Nobel Prize in Physics bridged the gap even further. It was awarded for experiments proving something that we once thought impossible. Quantum particles can actually pass through energy barriers, even in circuits that are large enough to see. The paradox of Steve and I is known as Wigner's friend, proposed by Eugene Wigner in 1961. It's one of the more direct confrontations with the nature of quantum measurement. The Wigner's friend paradox is like watching the same show with your friend, then meeting up the next day to compare your notes. But during the meeting, you both realize your endings were totally different. Both of you are convinced that what you watched was the real ending, and until you compare the notes, nobody really knows the objective truth. That's one of the ways quantum mechanics is dead tricky to observe. However, with a little switch in perspective, you can actually gain some helpful benefits from its strangeness. Take the quantum Zeno effect, for example. You know how observation makes a wave turn into a particle? Well, what if you just kept observing a quantum system constantly, making sure it never evolves into anything? It sounds random and frankly unnecessary, but there are scenarios where this could stabilize fragile quantum systems. In quantum computers, this kind of use case is a lifesaver. For example, what if there was a radioactive atom in an unstable quantum system? If left untouched, the atom would decay, and the effects of its radioactive properties could destroy that system. However, when you decide to frequently measure its state, like, say, every microsecond, that atom's evolution would be slowed so significantly that it couldn't get the chance to decay. It's like having a boiling pot that stops boiling when it's watched. The crazy part is that this has been experimentally verified in reality. When you engage with quantum physics, it's almost like there's a whole new world out there to mold. Sure, quantum mechanics has weird, mind-boggling rules, and yes, absolutely. But in the grand scheme of existence, humans have always found ways to tame that weirdness. 400,000 years ago, the cavemen that discovered fire were probably in awe at the strange element dancing before them. Today, fire is a fundamental part of the human experience. I don't think we think about that much. In contrast, quantum mechanics were only discovered in the mid-1920s. Yet, we are already starting to find ways that it can help us as a species. That burning quest for knowledge could take us beyond the stars one day. Speaking of useful functions for quantum physics, let's find a bomb. Yep, and not just that. We'll get to find this bomb without touching it or even setting it off. The idea is that with quantum science, it's actually possible to obtain information about the presence of an object due to the absence of a certain interaction. It's a deduction on a very bizarre level. We'll use a device called the interferometer. This interferometer relies entirely on a single particle's wave nature to operate. For our example, we'll be looking at a photon's wave nature. Now, let's go inside the interferometer. Within, we see that a photon is fired at a crossroads called a beam splitter. At this quantum crossroads, the photon doesn't just choose one path, instead it acts like a ghost, splitting and traveling down both paths at once. That's superposition. To take things further, the two initial paths meet again at a second crossroads, directing the photon to one of two final sensors. We'll call these final sensors detector D and detector C. There are two possibilities at play from here. First, if there's no bomb, both ghostly versions of the photon travel their paths. Remember that it is in superposition. They meet back at the second crossroads. Here, they interfere with each other, like two waves overlapping in an ocean. Since they are perfectly tuned, they cancel each other out at detector C and reinforce each other at detector D. A perfect wave interference, meaning no bomb. When there's a live bomb on the path, it acts as a detective. So, if we are looking for a live bomb in a sea of dud bombs, we place an interferometer. Then, as the photon is traveling, the moment it encounters a bomb, it chooses one of two paths. Remember how quantum particles do that thing where they stop the superposition when there's an observer? Well, that's what we're taking advantage of. Now the particle has two paths in front of it. If the bomb blocks one path, the interference pattern collapses. Sometimes detector C clicks, and that can only happen if the path was blocked by the bomb. That means we would have successfully detected a live bomb without setting it off. In this second path, because the bomb forced a choice, only one path's worth of the photon arrives at the final crossroads. Remember that perfect wave interference that we mentioned? That's broken, because one part of the wave did make it to the end. Without the interference, the rules of the final crossroads change. Now the photon can either go to detector C or detector D. Detector C never lights up if the bomb is absent. So if we run the experiment, read the waves from the ghostly versions of the photon, we can infer two things. First, the bomb didn't explode. But if the interference breaks, then a live bomb must have been present to break it in the first place. Therefore, we found the bomb without ever touching it. There is one small problem. Using this method to check for a bomb, there is always going to be a 50% chance the bomb actually does go off. It's like the photon can choose where it goes, and we have no power to influence it. However, if it chooses the path without the explosion, it's still a higher chance of detecting a bomb without setting it off. This truly impressive feat is revolutionary, and here's a simpler version of this. It's a lot like finding out whether or not someone broke into your family home. Normally, when you ring the doorbell, your dog barks. This time, you ring the bell and your dog stays silent. Well, that doesn't mean you saw an intruder, but the lack of a specific action, like a bark, implies that something is wrong. When there's no information, we can sometimes learn more than we think. But what happens when we have a confirmed theory that says all information is erased? Can we still recover that information using quantum means? Well, as you might have guessed at this point, quantum mechanics claims that yes, in fact, we can. Bringing things back to Einstein will highlight his take on black holes. In the theory of general relativity, Einstein described a black hole as a region of space-time where the gravity is so intense that nothing, and keyword here, nothing, not even light, can escape once it crosses the event horizon. Black holes are quite simple. They possess three classical properties: the mass, angular momentum, and electrical charge. No one can escape. Nothing can escape once it falls into a black hole. Every form of matter remains, whether that's a person, a book, or a hard drive. All the complex information within matter seems to get irreversibly crushed and swallowed, leaving only three classical properties of the black hole. According to Einstein's general relativity, the information is effectively destroyed. Therefore, the past history of what fell in is completely irrelevant. Well, the quantum world says otherwise. Quantum mechanics works on a principle that information must always be conserved. It's like once something exists, its previous and future states are confirmed to also exist. Even if you burn a book, the quantum world says the book's existence doesn't cease. and you can actually confirm that the ashes before you were once part of a book. So if you know the current quantum state of a system, there's a possibility that you could calculate its entire past and future. You see how that messes with general relativity? According to the quantum rules, information in the matter that fell into a black hole must still exist somewhere, and it can't just vanish. And it sounds plausible, especially given all we've learned already about quantum physics. But, as always, there is one small problem. How can anyone prove this to be the case? Well, that's where physicist Stephen Hawking comes in. In the 1970s, he discovered Hawking radiation, a concept that marries general relativity with quantum mechanics. At the edge of a black hole's event horizon, quantum fluctuations constantly produce pairs of interesting virtual particles dubbed a particle and an antiparticle. Usually, these pairs instantly annihilate each other. However, near the event horizon, one particle may fall into the black hole, while its partner escapes as Hawking radiation. The escaping particle actually carries positive energy away from the black hole. Meanwhile, the falling particle carries negative energy into the black hole. If you wait for the black hole to lose mass and shrink for trillions of years, you can start waiting now, I'll pause you there, something cool happens. Once the black hole evaporates, it leaves only thermal Hawking radiation in its wake, like steam rising off a hot surface. As useless as thermal radiation might seem, that's where the paradoxical implications actually begin. Say your hard drive fell into the black hole. Two things would have happened to its quantum information at this point. It's either destroyed with the information vanishing, or it's preserved, somehow escaping via the random Hawking radiation. Now, if the information is truly destroyed, it violates the fundamental laws of quantum mechanics. That makes it paradoxical because the laws of quantum mechanics are undeniably true. On the other hand, though, preservation means that the Hawking radiation isn't truly random, but rather it has the complete quantum state of everything that has ever fallen in. Why is that a problem? Well, according to scientists, it challenges our current understanding of gravity. Finding a solution to this paradox demands a theory of quantum gravity, one that smoothly merges quantum mechanics and general relativity. And right now, doesn't exist. Quantum mechanics feels like it turns everything inside out and then upside down. With this black hole information paradox, there's no denying that quantum physics feel like a cheat code to the classical physics and its laws. But the problem is that cheating is a lot harder than actually finding answers that we can fit into our current reality. If you could always guarantee a win, would you choose to keep winning no matter what? Even if it meant that a version of you loses in every other reality? Let's picture a game of Russian roulette. This game is extra special because your gun is connected to the quantum world. Now, normally, quantum events feel like pure chance. Either an atom is decaying or it's not. The only way to truly confirm something is when it collapses into one result or the other. It's similar to a coin landing on heads or tails. The many worlds interpretation proposes something slightly different. It says that the coin actually never stops spinning. Instead, the universe splits. Yep. And it is going to get weirder, I promise. In this interpretation, when an atom is measured, reality divides itself into multiple paths. We have one universe where the atom doesn't decay, in another, the atom decays. Both outcomes are equally real and happening, but they happen in separate, parallel worlds that are completely cut off from each other and cannot communicate. It's admittedly a stretch to imagine this being the case, but it works as a test to stretch the boundaries of what quantum mechanics can achieve. To take things even further, let's go back to that quantum gun we talked about. So, you're sitting in a room with this weapon. The trigger is connected to a quantum device. If you pull it, the atom within can either decay or not decay. If the atom decays, the gun fires a lethal shot. If not, the gun just clicks and you're good. You're determined to pull it 100 times in a row. No matter who or what the gun is pointed at, something unnerving will always happen. Now, if there's a friend watching you on a monitor, there are 2 points of view at play. The normal point of view is that your friend sees the bullet go off about 50% of the time, watching in grim resolve the horror of it all. After all, the odds of 100 trigger pulls being non-lethal are impossible, right? However, if your friend is watching in the many worlds view, they see the universe split with every pull. After the first pull, the friend sees 2 universes. After 100 pulls, they are now looking at trillions of possible universes. In the vast, overwhelming majority of them, the gun went off. But let's go back to your perspective with this special gun. In the many worlds view, you only ever experience the pulls where the gun doesn't go off, because those are the ones that you survive and continue to perceive. Your consciousness can only keep existing in branches where the gun never went off. I think that's obvious. So each time you pull the trigger, 2 things happen. Branch A, the gun fires. Your experience in that branch suddenly and violently ends. In branch B, that gun doesn't fire. Instead, you hear a click and you live, and you continue to experience. Every time you pull the trigger in this many worlds view, reality splits, and from your point of view, the gun is always clicking. Subjectively, you experience 100 times where the gun does not go off. But in reality, there are trillions of timelines where it did, and, well, tough luck. This quantum immortality twist tells us that in the many worlds view, your conscious awareness is like a ghost that automatically shuffles into one of the rare universes where you continue to exist. This isn't necessarily a recipe for immortality, let's just check you at the gate there. But when you think about it deeply, it evokes this bizarre feeling. By this logic, everyone alive would only be here at the cost of trillions of universes where they're not. Every moment where you hesitate to cross the street, every time you stepped in front of a car, countless other versions of you met a much different fate. Quantum physics shows us that reality is far stranger than our everyday experience reveals. From Schrödinger's cat to the many worlds interpretation, the universe isn't a concept that we can fully grasp in a classroom. The truth is much more complicated than we let on. Things can exist in multiple states at once, and observation itself can actually shape reality. Now, here's the fascinating part. Despite its strangeness, quantum mechanics isn't just abstract, it's the foundation of the world that we live in. The device in your pocket, every bit of modern technology, are all part of what pushes humanity forward. These weird, counterintuitive rules may scramble our minds, sure, but they are still fundamentally a part of our life. And by embracing that strangeness, we have the key to understanding the universe and ourselves. Here is what we now know. Particles are entangled across space, and before observation, they don't hold single definite states. They hold all of those states at once, collapsing into one only when they're measured. The universe, at its most fundamental level, is not a collection of things. It's a collection of possibilities, resolving into facts only when something interacts with them. For most of the 20th century, physicists sat with this and called it beautiful and troubling and almost entirely theoretical. The strangeness lived in the math, in particle accelerators, in thought experiments involving cats in boxes. Then someone asked a different kind of question. Not what does this reveal about reality, but what could we build with it? Because if a particle can hold multiple states simultaneously, and if entangled particles respond to each other instantly, regardless of distance, then a computer built on those principles wouldn't work the way every computer ever built has worked. It wouldn't move through possibilities one at a time, checking in sequence. It would hold all of the possibilities at once and resolve toward the right answer the way a quantum system resolves under observation. And that machine exists. It's being built right now. And the problem is not that it doesn't work. The problem is that it does. Because there's a system that has quietly protected almost every sensitive piece of information on Earth for the last 40 years. And it was designed assuming that some problems are simply too hard to solve quickly. A quantum computer disagrees. Google, Microsoft, IBM, the biggest tech companies in the world are all quietly preparing for a single threat, one that could crumble the entire digital infrastructure that we've built for the past 70 years. Right now, the entire planet is dependent on a digital system whose foundations are about to collapse. That's every secret, every transaction, every private message compromised. They all rely on a mathematical assumption that is close to its breaking point. The Q day, as experts call it, is the day when quantum computers are finally unleashed and they break every form of encryption that we have ever developed. The day when digital computing comes to an abrupt end. So, is this threat even real? And if it is there anything that we can do to stop it? To understand why quantum computing is such a big deal, you first have to understand what every computer you've ever used is built on. From the phone in your hand to the computers guiding spacecraft through deep space, everything runs on binary. At the lowest level, it's just ones and O's, tiny electrical switches being turned on and off billions of times per second. Every message you send, every video you watch, every AI model you interact with is ultimately reduced to long strings of these very simple bits. Classical computers are incredibly powerful, but they all share this same limitation. Each bit can only ever be one thing at a time. You're either a 1 or a 0 and never both. Quantum computers break that rule. Instead of bits, they use qubits. And thanks to the strange laws of quantum physics, a qubit doesn't have to choose between being a 1 or a 0. It can exist in a superposition of both at the same time. And that's not a metaphor or an analogy, that is literal. That one difference changes everything. Because when you scale this up, a classical computer has to check possibilities one by one. Is this 1 or 0? Okay, move on. Is this 1 or 0? Each one at a time. A quantum computer can explore many possibilities all at once. It's not just faster in the normal sense, it's like it's working in a higher dimension. And this is exactly why classical computers can't simply catch up. No matter how fast you make them, they are still bound to binary. They're still flipping switches between 1 and 0 step by step. Quantum computers aren't doing that at all. They're leveraging the fundamental rules of reality itself to process information in parallel across a vast space of possibilities. Which means there are certain problems, especially ones involving massive combinations or complex cryptography, that classical computers would take thousands, even millions of years to solve, but a sufficiently powerful quantum computer could solve in minutes. Unfortunately for our entire digital world, complex cryptography is what current encryption algorithms depend on. Modern encryption, which is the thing that protects your information from getting accessed by anyone on the open internet, is built on complexity and not secrecy. The idea is pretty simple. If someone knows how your encryption works, breaking it would require testing an astronomical number of possibilities. For a classical computer, that could take thousands or even millions of years. But for a sufficiently advanced quantum computer, it could take hours or even minutes. Q-Day is the hypothetical day that quantum computers will be powerful enough to do just that. When that day comes, you can say goodbye to private messaging, secure online banking, and digital privacy of any kind. Now, none of this is new. We have been building quantum computers for the past 2 decades, in fact, and for most of that time, cryptographers believed we still had at least another decade before machines powerful enough to break encryption would exist. But that timeline may have just collapsed. In December 2024, Google unveiled something called the Willow chip, a 105 qubit quantum processor that marked a major leap forward, not just in scale, but also in stability. You see, the biggest hurdle in quantum computing is errors. Qubits are incredibly fragile. The moment they interact with their environment, they lose their quantum state. This is called decoherence, and it's been the single biggest obstacle to building useful quantum computers. For years, adding more qubits just meant adding more noise, more instability, and more failure. But Willow seems to have changed that. Google demonstrated a benchmark designed to test whether a quantum system could reduce errors as it scales. The task itself wasn't practical. It's known as a random circuit sampling problem, essentially generating and verifying patterns that are extremely hard for classical computers to simulate. It's by no means useful in the real world, but it's one of the best ways to measure raw quantum capability. And Willow didn't just pass the test, it showed that as the system grew larger, error rate actually improved. And that's something we have never seen before. It means that we may have crossed a threshold from experimental machines that barely work to systems that can start becoming reliable. The benchmark took Willow 5 minutes. A classical supercomputer attempting the same calculation would take around 10 septillion years. That's 720 quadrillion times longer than the age of the universe. Naturally, this set off alarm bells across the tech world. The kind of breakthrough many hoped was still far, far away suddenly felt very, very close. In February 2025, Microsoft made its own move. The Majorana 1, a different bet on the same problem that Google was trying to solve. Microsoft's chip uses a design called topological qubits. They argue that these new qubits are inherently more stable than the ones used by Google. This is significant for one big reason. The industry is now beginning to compete on its architectures, and that means better designed quantum computers. Now, IBM has publicly committed to a roadmap for a more efficient kind of quantum system by the end of the decade. Fault-tolerant quantum systems. These are systems that produce concrete results without being obstructed by errors. And the race in this process isn't just American. China is taking this even more seriously than the West has acknowledged. With $15 billion in quantum research and its own milestones, there's a geopolitical race brewing for the future of computing. AI poses a present risk, but it doesn't break encryption. But quantum? It's the only technology whose progress is simultaneously creating an existential threat to all the digital infrastructure that we have. Now that companies are actually scaling quantum investments, there's still one thing lingering on everyone's minds. What exactly is being built? And what will it break first? Over the past 70 years, we've built our society on a specific kind of math. Trust, money, privacy, and power are tied to something that is on the brink of being dismantled. Yet the entire public doesn't even seem to know that this terrifying future is a possibility. If we can't even admit that the problem exists, how do we begin to confront it? Okay, so we've been talking a lot about how quantum computers are going to break encryption, but why is it? What exactly is the math that our current encryption system is designed on? So, imagine you are in charge of the biggest intelligence agency on Earth. Congratulations for your promotion. This means you get a virtually unlimited budget, unlimited time, and every supercomputer you can get your hands on. Today, you are tasked with but one mission: read one encrypted message. You're not going to steal it, you cannot intercept it. Your organization's duty actually sounds a lot simpler than a typical intelligence mission. So, how do you go about reading it? Now, here's what you are really up against. Say the message is protected by RSA-2048, the standard encryption method securing nearly every bank, every government communication, and every encrypted connection on the internet today. Underneath its complex exterior, it works on a single equation, a number that is hundreds of digits long and the product of two enormous prime numbers. Here's how it works. If I were to ask you to multiply two large prime numbers like 1007 and then 1009 You can pull out a calculator and get 1,016,063. But if I just gave you that same 1,016,063 and asked you which two prime numbers I multiplied to get it, well, that is going to take a lot of work. RSA-2048 takes the concept to a frustratingly high ceiling. Imagine prime numbers hundreds of digits long. Even the world's fastest supercomputers would take millions of years to configure the original primes that you need to multiply to get that impossibly long number. The number of combinations to test is larger than the number of atoms in the observable universe. So even if your intelligence agency has access to every classical supercomputer on Earth and the whole world banded together to ensure that this one message is read, by the most generous estimates, it'll still take about 1 trillion years to figure out. Your fancy agency would need to outlive the sun vaporizing the Earth roughly 40,000 times over. This isn't just some thought experiment, it is the literal security guarantee protecting your bank account right now. Now, give that same problem to a quantum computer running Shor's algorithm, and it finishes it in hours. In 1994, a mathematician named Peter Shor proved something the cryptography world did not want to be true. He developed a mathematical formula designed to run on a quantum computer. His formula directly targeted the impossible task of finding the two prime numbers from the longer number using something called superposition. If you've been watching our channel, then you're probably already familiar with the concept of quantum superposition. We've been doing a series on quantum physics, and it's been really fun. I'll leave the link to the playlist at the end of this video. But just a quick refresher, quantum superposition is the idea that a quantum particle can exist in multiple states at the same time. So a classical bit is a 1 or a 0. A qubit, however, can be 1, 0, or any combination of both simultaneously. Not because we don't know its state, but because it genuinely holds multiple possibilities at once. It's only when you measure it that it collapses into a single value. And this is where Shor's insight becomes a little troublesome. Factoring large numbers, the backbone of modern encryption, is hard for classical computers because they have to try possibilities one by one. Even the fastest supercomputers would take an absurd amount of time to break something like RSA encryption. But a quantum computer running Shor's algorithm doesn't approach the problem the same way. Instead of checking each possibility step by step, it uses superposition to explore many possible factors all at once. Then through another quantum effect called interference, it amplifies the correct answers and cancels out the wrong ones. Shor's algorithm has carried serious weight for 30 years now, but there has been one thing that has been holding it back. For the algorithm to actually work, it'll need a quantum computer with millions of stable qubits to break real-world encryption like RSA. Now, the Willow chip that was unveiled 2 years ago has just 105, so we are still in the safe zone for now, but still. The wall between us and the break is engineering, not physics or math. The math is beatable, and the physics is achievable. The day a quantum computer becomes powerful enough and stable enough to run Shor's algorithm against real-world encryption. It's the ultimate event for cybersecurity, as the geopolitical consequences will be instantaneous and have far-reaching ramifications. According to the Global Risk Institute's annual quantum threat timeline, Q-Day is going to arrive within 10 to 15 years. The US's NIST is operating on the assumption that a migration to post-quantum encryption must happen before 2035. National security agencies across France, UK, Germany, and other territories have also launched guidelines around it. The near-term effects are getting warmer and the collapse feels imminent. Every signed software update becomes forgeable, so your smartphone, your PC, your Mac updates can all be malware, and yet it can appear as if they came from Apple or Microsoft. Every website you visit becomes vulnerable. The comfort of seeing HTTPS in an address bar is gone, and your connections become readable to anyone looking to fish for your information or your online activity. And You may be wondering, how is any of this new? Here's the scariest part. The hacks that happen today require some level of social engineering and bait, where hackers attempt to disguise fake links and lead you to click on the wrong things. Every hack that happens today requires somebody along the chain to make a mistake. It's like forgetting to lock your house when you leave. On Q-Day, it'll be like everyone in the entire world instantly having access to a master key that opens all locks on Earth. Even if you follow the strongest conventional guidelines in the world, your data becomes trivial information for anyone running a capable quantum computer. Take cryptocurrency as an example. It's built on cryptography. It's right there in the name. And cryptography is exactly what quantum computers are designed to break. But the real danger isn't just what happens on Q-Day. It's what's already happening now. There are people quietly collecting encrypted data, old transactions, dormant wallets, entire blockchains, not because they can read it today, but because they believe they will be able to read it in the future. It's called harvest now, decrypt later. Many older wallets, especially ones using outdated cryptographic standards, are essentially ticking time bombs. The moment quantum computers become powerful enough, those protections disappear. These private keys can be derived, wallets can be opened, and it doesn't stop there. Even transactions happening in real time could become vulnerable, which creates a terrifying scenario. So imagine Q-Day hits, the news spreads instantly, people panic. They rush to move or sell their crypto before it's too late, but that reaction is exactly what attackers are waiting for, because initiating a transaction exposes information, and in a quantum world, that brief window could be enough. So the act of trying to escape the trap becomes the trap. A mass sell-off wouldn't just crash the market, it would turn into a feeding frenzy where every transaction is intercepted and every move exploited, like fish sprinting straight into a net that they can't see. Think about VPNs, data protections, cloud storage, company info, social security, all of that is within reach on Q-Day. The worst part is that Q-Day isn't a system failure. Companies will attempt to blame engineers and make a fall guy for its aftermath, but the bitter truth is that the math was beaten, and the assumption we've held for 70 years just simply stopped being true. The US's NIST has created its post-quantum standards, but actually getting people to follow them, that is another fight entirely. Migrating to these new standards means replacing the encryption that the entire internet sits on. It's like trying to replace a house's foundation without evacuating its residents. Most of the systems that need to migrate aren't even aware that the foundation is shaky, and that is a serious problem. Today, the world is happily entertaining AI debates on stages, flaunting CEOs that present themselves as visionaries of the future, but backstage, the cryptographic transition is a catastrophic headache that's driving classified briefings and conferences that most of the public has never heard of. There are institutions quietly preparing for what is coming, but the rest of us are going to be feeling the ripple effects of decisions that we never took part in. In 1989, after the collapse of East Germany, citizens formed the Stasi regime's headquarters and found 111 kilometers worth of paper files inside. Surveillance records on roughly 1 in 3 East Germans. For a population of 16 million, this was no trivial discovery. Conversations were transcribed, movements were logged, patterns of behavior were mapped out. Friends and family of citizens were exposed as informants. Throughout their regime, the Stasi maintained one of the most invasive surveillance states in modern human history, and yet they were limited. This was paper, typewriters, physical labor, and maintenance. All of these actions were necessary to keep their records. Surveillance had a hefty budget and a visible ceiling. There was a natural limit to how much of the state's population they could watch at any given time. Today, Major intelligence agencies generate more surveillance data in a single day than the Stasi collected over its entire 40-year existence. But at least, for now, your most private digital information still has a line of defense, and that is encryption. Even governments run into it. Apple, for example, has repeatedly refused to build a backdoor into its encryption, even under pressure from law enforcement and terrorism-related investigations. Their position has been consistent. If you build a backdoor for one case, you create a vulnerability for everyone. So for now, there are limits, and these are hard limits. Even the most powerful institutions in the world can't simply access whatever they want. But that balance only exists because encryption works. Quantum computing threatens to remove that barrier entirely. Because once governments have access to sufficiently powerful quantum machines, they don't need the cooperation from Apple. They don't need backdoors, they don't need permission, they can just unlock it. At that point, encryption stops being a safeguard and becomes a delay, a temporary obstacle between data being captured and data being read. And remember, a lot of that data is already being collected, stored, and archived, just waiting. So the real question isn't just what governments will be able to see in the future, it's what they've already seen, but simply haven't been able to read yet. It's like Schrödinger's data, which is very fitting for a discussion about quantum computers, if I do say so myself. Cryptography protects journalists, lawyers, whistleblowers, and ordinary people from authoritarian states. In the same breath, it also lets those same states keep their own secrets perfectly. Math never picks sides. Q-Day is the hammer that breaks both sides simultaneously. Whether that's a loss or a correction of an error, the institutions building the future are yet to decide, but neither has anyone else. The internet works because every system has good enough reasons to trust across borders. Your laptop in Sao Paulo can verify that a server in Hong Kong is who it claims to be because they both speak the same cryptographic language. That feature is what made the global internet possible. Post-quantum cryptography flips our expectations in a messy way. Not everyone will migrate to safer quantum-proof designs. Instead, it will be a slow process that knocks global economics off balance. Major banks will migrate first. EU government systems will follow, and then we'll see the same happen to wealthy nations and their critical infrastructure. Later on, smaller institutions, developing economies, and legacy systems may attempt to migrate, but that might be much later, if ever. When systems migrate at radically different speeds, the trust between them shatters. The single global internet we've taken for granted for 30 years will fragment into tiers. Today, when you buy something online from another country, the transaction happens in seconds. Your laptop talks to Amazon, Amazon talks to MasterCard, MasterCard talks to your bank talks to a settlement system, a device on the other side of the world ships towards you. Dozens of digital handshakes across multiple borders, all happening so fast that you don't notice them. And every one of those handshakes works because every system in that chain speaks the same cryptographic language. In a new post-quantum internet, those systems don't all migrate at the same time. Some networks become quantum safe and others stay exposed. When two systems try to connect, the security of the connection is only as strong as the weakest party in the chain. So your bank may have migrated, your bank's counterpart in another country may not have. The settlement system between them may be running on borrowed time. The device shipping to you may pull software updates from a network that's behind the curve. What you experience is not necessarily a more expensive transaction, it's a more fragmented one. Some routes work, others slow down, some break entirely. A purchase that moves seamlessly across 5 jurisdictions today isn't going to be the same. In the future, it has to find a path where every link in the chain has caught up with the same cryptographic standard. This is the issue. Today's interconnected world works largely because we can all understand the foundations built on binary. When quantum genuinely becomes a thing, those foundations stop being shared and the world stops working the way we've taken for granted. It's all beyond speculation at this point. Back in the day, cryptographic transitions reflected a similar pattern. When digital security moved to AES and then SHA-256, it took many years and lots of legacy systems were exposed. Currently, the necessary migration to post-quantum protection is being described as the largest infrastructure project in the history of the internet. The internet has worked the same everywhere for the past 3 decades, and that uniformity is what made it so strong. But that is about to end. What comes next isn't the death of the internet, no, it's the death of the old internet. A post-digital age is guaranteed to come, and it will look like a tiered network, secured within its own self-sustained walls. Everything outside of these walls will feel like a dangerous wasteland. Whatever happens in that future won't be the hopeful idea we briefly believed the internet was. Everything covered so far is what quantum breaks, but they're not just engines of destruction. It's not all gloom and doom. They're also capable of some really powerful and awesome things. The math behind the digital age, binary, is actually incredibly good at a lot of things. It's super reliable, it's very precise, it's perfect for logic-based operations. That's why it powers everything from search engines and video streaming to financial systems and our modern AI. It excels at structured problems, step-by-step communications, and tasks where outcomes can be broken down into clear sequences. And binary is the reason that we have the internet. The reason we can simulate rockets, edit films, and build entire virtual worlds. It's not a limitation in most of the domains we live in today. But that same structure is also where it starts to break down. There are entire categories of problems that don't fit neatly into a step-by-step logic. Problems where the number of possibilities explodes so quickly that even the fastest classical computers hit a wall. Things like accurately simulating molecular interactions, understanding complex chemical reactions, or solving certain advanced physics problems. These aren't just hard problems, they scale in a way that makes them practically impossible for binary systems to handle in a meaningful time frame. And no matter how much we improve classical computers, faster processors, more memory, better architecture, we are still working within the same fundamental framework. Are you familiar with Moore's law? If not, here's the simple version. It's the idea that the number of transistors on a chip doubles every couple of years, making computers exponentially more powerful over time. For decades, that trend held, but now it's starting to break. We've shrunk transistors to the point where they're only a few atoms wide. At that scale, electrons stop behaving like clean, predictable signals. They begin to tunnel, to blur, to exist in probabilities rather than certainties. The stability that classical computing depends on starts to break down at that level. In other words, we don't just run into an engineering problem. We ran into the limits of physics itself. And that's where everything changes, because quantum computing isn't just a faster version of what we already have. It's what happens when we stop resisting those quantum effects and start using them instead. It's not a replacement for classical computing, and it's more of a leap beyond the boundaries that defined the digital age in the first place. Which means the real story isn't just what quantum breaks, it's what it unlocks too. In a post-digital world, we'll be stepping into entirely new categories of problems. Problems that classical computers were never going to solve, no matter how much time or power we threw at them. The cryptographic collapse we've been talking about is really just a side effect. It's a consequence of a much larger shift. Q-Day is the deadline. It's urgent, and it's disruptive, and it's very real, but it won't be the main event. Because beyond that one moment is where things are actually going to start getting really interesting. And one of the clearest examples is a field that's quietly been hitting a wall for years, a wall that most people didn't even realize exists. Designing new medicines sounds like something we should have mastered by now. We have supercomputers, massive biological data sets, and AI systems that can predict protein structures with remarkable accuracy. And yet, creating drugs is still slow, it's expensive and heavily dependent on trial and error. That's because, at its core, it is a quantum problem. Every molecule is governed by quantum mechanics. The way atoms bond, the way electrons interact, the way a drug binds to a target in the body. All of it depends on complex quantum behavior. To truly understand it, you need to simulate those interactions precisely. And classical computers can't do that at scale. The number of possible configurations grows so quickly that even our best systems are forced to approximate. So instead of knowing what will work, we make educated guesses, we test, we fail, and then we repeat that process over and over again. This is why big pharma industry giants like Roche, Pfizer, and AstraZeneca have all launched quantum computing programs. Google DeepMind's AlphaFold revolutionized protein structure prediction by using classical AI. Yet, the founders themselves have admitted that the next frontier will actually require quantum computing for molecular interactions. Today, our industrial civilization revolves around a small number of materials. This status quo has been considered good enough for the past century. Lithium-ion batteries power a lot of our energy, but their chemistry also hits a theoretical limit. Solar cells only convert a fraction of incoming light. All this time, we've been optimizing inside the constraints of the materials that we found, not the materials that we designed. Quantum genuinely gives us the ability to develop new materials at the molecular level and to build them fit for purpose instead of just finding them by accident. Currently, we have some examples of phenomena that we are aware could change our lives, yet we just don't have the right technology to make the changes stick. It's like capturing lightning in a bottle. For example, actually, there's a bacterial enzyme capable of trapping nitrogen from the atmosphere, and it could do this at room temperature without industrial input. The problem? We can't model it, because the molecule is too quantum mechanically complex. Microsoft's research division has published a quantum simulation of this enzyme as a target application for an eventual quantum computing future. When it's possible, we would revolutionize fertilizer production and reduce its effect on global energy supplies. We would be designing a new relationship with our physical world, one where we design materials from first principles instead of optimizing within the constraints of what we've happened to find. Quantum directly addresses a whole class of decisions in the modern world. So far, we've only been able to solve the problems we encounter in an approximate sense. Stuff like routing packages, allocating national budgets, and balancing loads and power grids. Approximate solutions cost the global economy enormous sums of money in waste, inefficiency, and missed allocations. Even with all that in mind, we have been doing a decent job. It's impressive. For certain types of optimization, quantum computing will provide solutions that have never been seriously considered prior, and the applications span industries. Today, Goldman Sachs and JP Morgan are exploring quantum optimization for portfolio risks. Similarly, other companies from airlines to car manufacturers are looking to apply quantum research in their designs. Once we scale to quantum, we'd be living in a world that runs on better math. Supply chains will route more efficiently, financial systems will allocate capital more precisely, power grids would light up the world without burning its resources completely. Most of these gains are invisible to consumers, but the final effect is a civilization that operates closer to its mathematical limits than what was possible in the digital age. Unlike what we have today with smartphones, laptops, and tablets, quantum hardware isn't going to be a commercialized experience for every citizen. There's no quantum laptop coming. These machines are too expensive, too fragile, and require cooling in temperatures colder than deep space. They'll also be operated by a tiny number of institutions. In a nutshell, access to quantum is limited due to physics, and this will be the biggest challenge. Today, there is some meaningful quantum computing in existence. If we zoom out, it's fair to say that quantum hardware is only present in a few dozen institutions globally. As for the rest of the world, and the billions of people, hundreds of governments, millions of companies, well, access to quantum would only be possible through intermediaries, middlemen that dictate how, when, and why everyone else can use it. At the peak of our digital age, we managed to put a supercomputer in the pockets of half the planet. In the post-digital age, at least at the start, the most powerful tool ever built will be behind the walls of a few dozen institutions. Thanks to all the doom and gloom of AI, a question at the forefront of everyone's mind when faced with quantum computing is, will this replace my job too? And it's a fair concern, but it's a lot deeper than what AI affects. Quantum's replacement is more targeted at institutions than anything else. Take pharmaceutical companies, for example. The ones with quantum access will completely outclass competitors without any access. It's the same with banks and governments. This displacement is at scale, so the reactions from governments and other large entities would be more of a concentrated effort to prevent it. With AI, your local representative doesn't care that you lost your coding job, but when quantum threatens the existence of a government itself, well, there's nothing more necessary than confronting the change together. Right now, the decisions being made are the following. Who funds quantum? Who controls the supply chain for the rare materials it requires? Who licenses the hardware? Who sets the standards? Who trains the workforce? All of these questions are being asked and answered in rooms most people will never enter, by people we will never see, with consequences that will outlive us all. For all of its flaws, the digital age was the ultimate democracy for technological power, but the post-digital age is being built differently. And who gets to build it is what determines the kind of civilization that we will get in the new age. The only question left is whether we are awake enough to shape this future too. You're standing in a doorway right now. Behind you is a room you've lived in for the past 70 years. Every smile, every fight, every love and heartbreak was witnessed by this room. Ahead of you is another room, one that isn't fully visible. From where you stand, you can feel a sense of hope. A genuine feeling that this new room is where you were always heading towards. But it's being built right now by people you don't know, with materials you don't understand. Living in this doorway means something specific for us. It means trusting systems whose foundations have an expiry date known as Q-Day, sending messages already being recorded by people waiting to read them later, watching your future being decided without your input. The room behind you is closing on its own. The room ahead of you is being built whether you step into it or not. For now, all you can do is exist in a state of superposition, not knowing whether to be excited or terrified about the future until you can observe it for yourself. And isn't that what quantum is all about? So we've taken the logic of the quantum world and begun to build on it. We've looked at superposition and entanglement, two features of reality that make no intuitive sense, and pointed them at the hardest computational problems that we have, at encryption, at drug discovery, and material science. We treated the strangeness as a resource. But there's a question that has been accumulating beneath every single subject so far. One that the physics keeps approaching and then pulling back from, as if it's not quite ready to say it to us out loud. We've talked about observation collapsing the wave function, about the act of measuring a particle, forcing it to choose a state. We've used words like observer and measurement and treated them as though they're neutral, as though a camera and a human eye are doing the same thing. But what if they're not? Some physicists, serious ones, not fringe ones, looked at the measurement problem and followed it all the way to its edge. And at that edge, they found a conclusion they could not easily dismiss. There's a quiet embarrassment at the center of modern quantum physics. It's rarely mentioned outside academic circles, and when it is, it's often softened with abstractions or confusing mathematical language, but the problem itself is pretty blunt. According to our most successful physical theory, reality does not fully exist until it's observed. Quantum mechanics, unlike classical physics, doesn't describe objects as having definite properties at all times. Instead, it describes them with a mathematical entity called a wave function. This wave function doesn't tell us where a particle is or what it's doing. It just tells us what the particle could be doing. Multiple positions, multiple states, multiple outcomes, all covered by the wave function all at once. This condition is called superposition, and it does work mathematically. The predictions derived from it are so accurate that nearly all modern technology depends on them. Transistors, lasers, MRI machines, and even GPS systems, they all rely on quantum principles. So the theory isn't speculative, it's precise, it's testable, and most importantly, it is overwhelmingly successful. And yet, it contains within it a fundamental fracture. When a quantum system is not observed, it evolves smoothly according to the Schrödinger equation. Nothing dramatic happens and all its possibilities coexist. But the moment a measurement is made, the wave function collapses. One outcome becomes real while all the other outcomes vanish. And the problem isn't that this is happening. The problem is that quantum mechanics never explain how or why it happens. And this is known as the measurement problem. In classical physics, measurement is passive. A thermometer does not create temperature. A ruler does not create length. They reveal properties that were already there. Quantum mechanics breaks this assumption. Before measurement, properties are not merely unknown, they are undefined. The act of measurement does not reveal reality, it appears to create it. To avoid confronting this directly, early physicists adopted what became known as the Copenhagen interpretation. In this view, quantum mechanics does not describe reality itself, it only describes our knowledge of reality. Asking what a particle really is before measurement is considered meaningless. Reality, in this framework, is inseparable from observation. And for a while, this philosophical retreat was tolerated. The math worked out, and the predictions were correct. But one question adamantly refused to stay buried. What exactly then counts as an observation? This question becomes unavoidable when you follow the measurement chain carefully. A particle interacts with the measuring device. The measuring device interacts with the detector. The detector produces a signal. The signal is processed by electronics. The electronics produce data. The data is then displayed on a screen. Light from the screen is entering your human eye. Neural signals travel to the brain, and somewhere along this chain, the wave function stops evolving smoothly and collapses into a single outcome. Well, where in that chain does that transition occur? Well, physicist John von Neumann formalized this problem in what is now called the von Neumann chain. His analysis showed that mathematically every physical component of the measurement process can be treated as a quantum system. The measuring device does not escape superposition, neither does the detector, and neither does the brain, and so on, at least in principle. If you treat all physical systems consistently, well, the chain never breaks. Unless something non-physical intervenes. Von Neumann's conclusion was not mystical, but it was unsettling. He suggested that the only place the collapse could occur without contradiction is at the level of conscious awareness itself, not at the instrument, not at the brain as a physical object, but at the moment you experience that observation. And I don't think I need to say, but this idea was not embraced enthusiastically. It was tolerated at first, but then quietly ignored. But it never fully disappeared because the logic behind it was difficult to refute. Eugene Wigner sharpened the problem with a now famous thought experiment. Imagine a friend in a sealed laboratory measuring a quantum particle. Inside the room, the friend observes a definite result. Outside the room, you have no access to that information, and from your perspective, the entire lab, including the friend, must be treated as a quantum system. That system evolves into a superposition itself. The friend is seeing result A, and then the friend seeing result B are both technically for you, happening at the same time. Now, if you eventually open the lab to see the result that your friend got, when did that collapse happen? Was it when your friend first looked at the result, or was it when you learned what your friend saw? If consciousness is what causes that collapse, then the answer depends on whose consciousness counts as the true observer. If the friend's observation collapses the wave function, then from your perspective, collapse happened without your knowledge or your observation. However, if collapse requires your awareness as friend B, then your friend A existed in a superposition until you opened the door or asked the question. And frankly, both options are disturbing. One implies that reality is observer-dependent. The other implies that even conscious observers can exist in superposition. Wigner himself took the problem seriously. For a time, he openly argued that consciousness must play a fundamental role in physics. Later in life, he softened his position, but he never resolved that paradox. So this is where physics collides with another unresolved problem, this time from neuroscience and from philosophy. Even if we set quantum mechanics aside, consciousness itself is not well understood. Neuroscience excels at explaining mechanisms. Neurons fire, signals propagate. Networks process information. You damage a region of the brain and specific functions are lost. These correlations are robust and very well documented. But why does neural activity produce subjective experience? Why is there an inner world at all? Why does information processing feel like anything from the inside? This is known as the hard problem of consciousness, and it is not a gap in the data, it's a gap in our ability to explain. A computer can process information, recognize faces, generate language, and outperform humans at complex tasks. But no amount of functional description explains why redness feels red, why pain hurts, or why awareness exists as a first-person phenomenon rather than a third-person process. Classical physics describes systems from the outside. Consciousness is known only from the inside. And this mismatch has led some researchers to an uncomfortable conclusion. If consciousness cannot be reduced to classical computation, and if quantum mechanics already requires an observer-like role to explain how reality becomes definite, then perhaps these two problems aren't separate. Perhaps consciousness is not an emergent afterthought in a mechanical universe, but a missing piece of its foundation. Now, this does not mean that consciousness is magical or supernatural. It means that our current picture of reality may be incomplete in a way that excludes the very thing doing the observing. So the question then is not whether consciousness is mysterious. The question is whether a universe described entirely by blind mechanical laws can ever account for the fact that it is being experienced at all. The physical mechanism, how the brain might escape classical computation. If consciousness truly has something to do with quantum mechanics, then the claim cannot remain philosophical. It has to interact with the physical world, it has to stand up and be tested, and it has to explain how a biological organ operating at body temperature could participate in phenomena usually reserved for subatomic particles. Otherwise, the idea collapses into nothing more than a metaphor. Roger Penrose, a mathematician disturbed by this limitation that most people would never even notice, explained that the starting point is not the brain, computation is. Modern neuroscience is largely built on an assumption inherited from computer science, that the brain is, at its core, an information processing machine. Consciousness, in this view, is what it feels like to run a sufficiently complex algorithm. Penrose rejected this assumption on mathematical grounds. His argument, hinging on Gödel's incompleteness theorems, results from mathematical logic that places strict limits on formal systems. Gödel showed that any sufficiently powerful logical system will contain true statements that cannot be proven within the system itself. No matter how complete the rules seem, there will always be truths that escape mechanical derivation. Penrose noticed something unsettling about this. Human mathematicians can see the truth of certain statements that no algorithm can formally prove, not by brute force calculation, but by insight, by understanding. If human understanding were fully equivalent to an algorithm, then humans would be bound by the same limitations as formal systems. Yet, in practice, they're not. They can step outside the system, recognize its structure, and grasp truths that the system cannot certify. Penrose's conclusion was not that humans are magical. It was that human understanding is not computable. It cannot be reduced to a classical algorithm running on biological hardware. If that is true, then the brain is not functioning like a digital computer. And if it isn't classical, then it must be doing something else. Penrose proposed that the something else lies in quantum physics, but not in the usual way that people imagine. Not random quantum noise, not vague mysticism either. A very specific process built into the fabric of space-time itself. In standard quantum physics, wave function collapse is treated as a rule. You observe the system and the probabilities become facts. But Penrose found this deeply unsatisfying. It relies on measurement without explaining what measurement fundamentally is. Instead, he proposed that collapse is a real physical process called objective reduction. The idea is simple. According to general relativity, mass and energy curve space-time. According to quantum mechanics, particles can exist in superposition. But if an object is in two places at once, then space-time itself must also be in a superposition of two different geometries. Penrose argued that space-time cannot tolerate this indefinitely. Beyond a certain threshold, the superposition becomes unstable and then collapses on its own. No observer required, no measurement device, just gravity enforcing consistency. And this collapse is not subjective, it is objective. It happens whether anyone is watching or not. And crucially, Penrose proposed that each such collapse corresponds to a moment of conscious experience. At this point, the theory needed a brain. Penrose understood physics, but he did not know where such quantum processors could occur in neurons. That is where Stuart Hameroff enters the picture. Hameroff is an anesthesiologist, not a physicist. His interest in consciousness came from an unusual direction: anesthesia. General anesthetics reliably erase consciousness while leaving most neural processing intact. Patients can still have brain activity, reflexes, and even memory encoding under certain conditions. What disappears is subjective experience itself. Hameroff noticed something strange in this. Anesthetics did not primarily target synapses, action potentials, or large-scale neural signaling. Instead, they bound preferentially to structures inside neurons called microtubules. Microtubules are part of the cell's internal skeleton. They give neurons their shape, transport materials, and organize intracellular processes. For decades, they were considered structural scaffolding, important but not informational. Now, Hameroff suspected otherwise. Microtubules are made of repeating protein units arranged in a highly ordered lattice. At very small scales, this lattice resembles a crystal. And crystals, under the right conditions, can support coherent quantum states. Together, Penrose and Hameroff proposed orchestrated objective reduction, or ORC-OR. The idea is that microtubules act as quantum information processors. Within their lattice, components can exist in superpositions functioning as quantum bits rather than classical ones. These superpositions evolve coherently for a brief period, orchestrated by the brain's neural activity. When the superposition reaches Penrose's gravitational threshold, it undergoes objective reduction. The collapse is not random noise, it is structured, shaped by the geometry of space-time itself. Each collapse produces a discrete moment of experience. Consciousness, in this model, is not continuous. It is a sequence of quantum events. A rapid series of collapses, often described metaphorically as moments or frames, occurring roughly 40 times per second. Now, this would explain several otherwise puzzling features of experience. The unity of consciousness, the suddenness of insight, the way awareness feels discrete yet seamless. Even the temporal binding problem, how different sensory inputs are experienced as a single moment. For decades, this theory was dismissed for one simple reason. The brain is warm, wet, and very, very noisy. Quantum coherence is fragile. In laboratories, it typically requires extreme isolation and near absolute zero temperatures. In the brain, your molecules are vibrating, ions are flowing, and thermal noise dominates. Any delicate quantum state should decohere almost instantly. So, ORC-OR seemed dead on arrival. But biology has a habit of exploiting physical effects in ways physics does not expect. In the early 2000s, researchers studying photosynthesis discovered something surprising. Energy transfer in plant cells showed signatures of quantum coherence. Excited electrons explored multiple paths simultaneously, selecting the most efficient route through superposition at room temperature. So quantum biology was no longer just hypothetical. In comes anesthesia research. Experiments showed that anesthetics disrupted microtubule function in ways consistent with interference in quantum-level processes. Consciousness disappeared when microtubule dynamics were altered, even though large-scale neural firing could remain. More recently, studies have suggested that microtubules may support a phenomenon known as superradiance. In very simple terms, this allows many quantum components to act as a single coherent system, amplifying and stabilizing quantum effects rather than letting them decay. This matters because it addresses the central criticism to the theory. If microtubules can sustain large-scale coherence through collective behavior, then quantum processes in the brain are no longer obviously impossible. And let's just say right out here, none of this proves that OR is correct, but it does shift the question. The brain may not be a classical machine with quantum noise layered on top. It may be a system evolved to sit precisely at the boundary where quantum and classical physics meet. If that boundary is where reality becomes definite, then the brain is not just processing information, it is participating in the same processes that turns possibility into reality, which raises a final destabilizing thought. If the brain uses quantum mechanics not just internally, but relationally, through entanglement and non-locality, then consciousness may not be confined to the skull at all. The connection to the universe when the mind is no longer local. Up to this point, the discussion has remained uncomfortable but contained. Consciousness may rely on quantum processes. The brain may operate at a boundary classical physics does not describe well. These ideas stretch neuroscience, but they don't yet rupture our sense of personal identity. That rupture happens when non-locality enters the picture. Quantum mechanics does not merely allow strange behavior at small scales. It violates one of the most intuitive assumptions humans have ever held, that objects exist independently and that influence travels locally through space. Entanglement is the clearest expression of this violation. When two quantum systems interact, they can become entangled, meaning their properties are no longer independent. If you measure one and the state of the other is immediately constrained, no matter how far apart they are. This correlation is not mediated by signals traveling through space. It is built into the structure of the shared quantum state itself. Einstein found this intolerable. He called it spooky action at a distance, and this wasn't as praise, this was a warning. However, decades of experiments have confirmed entanglement as a real feature of the world and not a mathematical trick. The uncomfortable implication is this. The universe is not composed of separate things interacting across space. At the deepest level, it is a network of relationships that ignore distance entirely. If consciousness depends on quantum processes, then it does not merely occur within the universe. It participates in the same non-local structure that underlies all physical reality. This isn't poetry, it's a structural claim. In classical neuroscience, the brain is modular. Regions perform tasks, signals propagate. Information is localized. Consciousness, in this view, is an emergent summary, a story that the brain tells itself about its own activity. Quantum systems do not behave this way. They are unified. You cannot fully describe one part without referencing the whole. This raises a radical possibility. Consciousness may not arise from isolated computations inside the skull, but from coherent processes that bind the brain into a single quantum system. There are tentative experimental hints pointing in this direction. Researchers have long struggled to explain how the brain integrates information so seamlessly. Visual input, auditory input, memory, emotion, and bodily sensation, they're processed in different regions, yet experienced as a single moment. This is known as the binding problem. Classical explanations rely on synchrony and signaling, but synchrony alone does not explain unity. It explains coordination, but not experience. Quantum coherence offers a different mechanism. Entangled systems behaving as one system even when they are spatially distributed. Recent MRI-based studies have suggested correlations between distant regions of the brain that are difficult to account for purely classically. These correlations are not proof of entanglement in the strict quantum sense, but they do hint at deeper integration than standard models predict. If microtubules can sustain coherent quantum states, and if those states span large neural networks, then consciousness may be a genuinely unified physical process, not an illusion layered over fragmentation. And this has consequences beyond neuroscience. Quantum theory already forces us to reconsider the role of the observer. In the standard view, the universe evolves according to deterministic equations until a measurement occurs. Then, something then selects one outcome from many. The question has always been, what performs the selection? If conscious systems are themselves quantum systems, and if their awareness corresponds to objective reductions in space-time geometry, then consciousness is not a passive witness. It is an active participant in the unfolding of reality. This idea is sometimes called the participatory universe. This phrase might sound wishy-washy, but I assure you it's real science. It describes a universe in which reality is not fully defined without interaction. Observers are not external to the system. They are part of the mechanism by which the universe becomes specific rather than indefinite. In such a universe, consciousness does not merely observe events. It helps actualize them. This does not mean human minds can control reality at will. Quantum processes are constrained, probabilistic, and subtle, but it does mean that awareness is not an afterthought. The boundary between mind and world becomes more porous. Objects appear separate because decoherence hides their connections, not because these connections are non-existent. In that sense, consciousness may be local only in appearance. A conscious system may be anchored to a brain, but not confined to it in the way that classical intuition demands. Its underlying processes may be entangled with broader quantum fields, participating in structures far larger than the organism itself. Or, in layman's terms, your brain might just be connected to the universe. The feeling of being a self, located behind the eyes, observing the world from a single point in space, may be a useful interface rather than a literal description of the true nature of consciousness. A way of navigating a reality that is fundamentally non-local without being totally overwhelmed by it. At this point, the conversation does begin to drift away from conventional physics and towards more radical frameworks. But these frameworks didn't arise from mysticism. They arose from attempts to take quantum mechanics seriously all the way down. One such framework begins with a blunt evolutionary claim. If perception evolved for survival rather than truth, then the world you experience is not reality as it is reality as it's useful. And if that's the case, then space-time itself may not be fundamental at all. Radical alternatives when reality is no longer what it seems. At a certain depth, attempts to explain consciousness stop feeling like extensions of neuroscience and begin to resemble reconstructions of reality itself. The assumptions that once felt stable, space, time, objects, even causality, begin to dissolve under scrutiny. One of the most direct challenges comes from an unexpected place: evolutionary theory. Donald Hoffman approaches the problem of perception with a simple but unsettling premise. Natural selection does not reward organisms for seeing the truth. It rewards them for surviving long enough to reproduce. Accuracy is irrelevant unless it increases your chances of survival. From this, Hoffman derives a result that feels almost, frankly, offensive to common sense. If a species evolved to see reality as it truly is rather than as a simplified interface optimized for survival, it would be outcompeted and then eliminated. Truth is expensive. Illusion? It's efficient. In this framework, perception is not a window into reality, it's a user interface. Just as a computer desktop hides voltage, transistors, and machine code behind icons and folders, our senses hide the underlying structure of the universe behind space, time, objects, and causality. A chair is not a thing in itself. It's an icon representing something useful to sit on. A car isn't metal and engine and motion. It's an interface object, signaling either danger or opportunity, depending on whether you're inside the car or standing in front of it. The key implication is this: space-time itself may be a part of that interface. Hoffman argues that if space-time were fundamental, evolution would have no reason to hide it. The fact that our perceptions are spatial, temporal, and object-based suggests that these are not features of reality, but of the interface through which we interact with it. So, the question is, what exists beneath the interface? In Hoffman's model, the fundamental constituents of reality are conscious agents, not human minds, but minimal units of experience and decision. These agents interact, form networks, and generate the structures that we perceive as physical reality. Matter does not give rise to consciousness. Consciousness gives rise to the appearance of matter. This isn't panpsychism in the usual sense. Hoffman is not claiming that electrons have feelings or that rocks are secretly aware. He's claiming that what we call physical objects are emergent symbols, compressed representations of interactions between conscious systems that we cannot perceive directly. In this view, you are not a body that produces consciousness. You are a localized perspective within a much larger field of interacting awareness. The brain, then, is not the generator of experience. It's a part of the interface, like a VR headset worn by consciousness to navigate a particular slice of our reality. This idea aligns uncomfortably well with quantum mechanics. The observer-dependent nature of measurement, the breakdown of locality, the inability to define properties without interaction, all of these suggest that reality is relational rather than objective in a classical sense. But Hoffman's model still assumes one universe. Another interpretation takes a more drastic step. The many worlds interpretation of quantum mechanics begins with a refusal. It refuses to accept wave function collapse at all. Instead, it takes the mathematics literally. According to this view, the wave function never collapses. Every possible outcome of a quantum event occurs. When a measurement happens, the universe branches. One branch contains outcome A. Another contains outcome B. Both are real, they're simply not interacting. There's no special role for observation, no moment where possibility becomes actuality. Reality continuously differentiates. This interpretation solves the measurement problem by eliminating it. There's no collapse to explain, it only branches. But it introduces a new discomfort. If every possible outcome occurs, then there are versions of you who made different choices, survived different accidents, and died in many different ways. At every moment, reality fractures into countless paths. Most of these paths are unobservable to you, but some aren't. This leads to a disturbing philosophical extrapolation known as quantum immortality. Consider a thought experiment involving a lethal quantum device, often framed as a quantum Russian roulette. A trigger is pulled. A quantum event determines whether the gun fires. In many branches of the universe, it does. In some, it doesn't. From the outside, an observer sees death almost every time. From the inside, though, something strange is happening. Consciousness cannot experience its own absence. Try imagining just not being. You probably had difficulty because you can't. There is no subjective moment of being dead. So awareness continues only in branches where survival occurs. From your perspective, you always hear the click, but never the gunshot. Over repeated trials, the odds of your survival become astronomically small, but subjectively, survival feels guaranteed. So if many worlds is correct, then consciousness is biased towards branches where it continues, not because of fate or design, but because branches without experience are unexperienced. Now, this does not mean you are invincible. It means that from your point of view, you only ever find yourself in timelines where you remain alive until aging, disease, or gradual degradation erodes the conditions necessary for awareness. But even then, the implications remain unsettling. In this framework, death is not a single event, it's a distribution, a gradual thinning of branches where experience persists. Identity becomes fluid, continuity becomes conditional, and the universe becomes vast beyond comprehension, not just in space, but in possibility. At this stage, the idea of consciousness as a local phenomenon begins to feel inadequate. Whether through Hoffman's conscious agents or Everett's branching worlds, awareness appears less like a byproduct and more like a structural feature, something that does not sit neatly inside of space-time but uses space-time as one of its expressions. Now, let's pull back for a moment. These ideas are not proven, and many physicists reject them. Others tolerate them as philosophical interpretations with no testable consequences. But notice what they have in common. They all arise from taking quantum mechanics seriously without retreating into classical intuition. They all suggest that reality is not composed of objects but of processes, not of things but of relationships. Not matter first, but information, interaction, and experience. And they all converge on the same unsettling possibility: that consciousness is not an accident occurring inside the universe. It may be one of the ways the universe exists at all. All that remains is to step back and ask what this synthesis means and what it doesn't. Synthesis. What changes when the mind is no longer secondary? At this point, it becomes tempting to reach for resolution, to decide which theory is correct, which interpretation survives scrutiny, which framework deserves to replace the old one. But that impulse itself reflects a habit inherent from classical thinking, the belief that reality must collapse into a single clean answer. Well, quantum mechanics has taught us otherwise. There is no consensus on quantum consciousness. Orc-OR remains controversial. Many neuroscientists reject it as unnecessary. Many physicists remain skeptical that gravity-induced collapse has anything to do with experience. Hoffman's conscious agents are mathematically elegant but empirically distant. Many Worlds removes collapse but multiplies realities beyond intuitive tolerance. None of these views has won. And yet, something important has already changed. The question is no longer about whether consciousness fits neatly into the existing scientific picture. It doesn't. The question is whether the picture itself was ever complete without it. Classical physics gives us a universe made of objects, moving through space, evolving through time, indifferent to observation. Consciousness in that universe was an anomaly, an emergent side effect of sufficiently complex machinery, a late arrival, a byproduct. Quantum mechanics undermine that narrative at its foundation. The universe, at its most precise description, is not a collection of things with fixed properties. It is a structure of probabilities, relationships, and potentialities. Outcomes do not exist until something distinguishes them. The very act of defining what is depends on interaction. This does not prove that consciousness creates reality, but it strongly suggests that reality cannot be fully defined without accounting for the role of observation, perspective, and information. In neuroscience, a similar shift is underway. The brain is no longer viewed as a simple stimulus-response machine. It's predictive, integrative, and deeply context-sensitive. Experience is not passively received, it's actively constructed. If quantum processes play even a partial role in this construction, then consciousness is not merely running on top of physics, it's entangled with it. That entanglement carries consequences. It means the boundary between the mind and world is not as firm as it feels. It means the sense of being, an isolated self sealed inside a body and looking out at an external universe, may be a perceptual convenience rather than a fundamental truth. It also means that many familiar debates may have been misframed. The argument over whether consciousness is in the brain or beyond the brain assumes that location works the way that classical intuition says it does. Quantum mechanics does not respect that intuition, neither increasingly does biology. The argument over whether free will is an illusion assumes that causality flows cleanly from past to future. Quantum processes complicate that picture. So does the role of indeterminacy in physical law. Even the fear embedded in ideas like quantum immortality reveals something very, very important. It exposes how tightly personal identity is tied to continuity, memory, and narrative. If you strip those away, and survival becomes less reassuring, not more. What remains consistent across all these frameworks is not certainty, but displacement. The brain stops looking like a self-contained machine and starts looking like an interface. Consciousness stops looking like a private hallucination and starts looking like a relational phenomenon. The universe stops looking like a finished object and starts looking like an ongoing process. This does not mean that meaning is guaranteed. It does not imply purpose, destiny, or cosmic benevolence. Those interpretations are human additions, not scientific conclusions. What it does mean is quieter and more unsettling. It means that the deepest problem in science, the relationship between mind and matter, may not be solved by reducing one to the other. Reduction works when the parts are more fundamental than the whole. Quantum theory suggests that in some cases the whole defines the parts. If that's true, then consciousness may not be something the universe accidentally produced. It may be, maybe, one of the ways the universe differentiates itself. Not a ruler standing outside reality, measuring it, not a ghost haunting matter, but a process through which potential becomes experience. And that idea resists closure. It refuses a final, comforting answer. It sits uncomfortably between physics and philosophy, between experiments and introspection. And you know what? Hey, maybe that's the point. The mistake may have been expecting consciousness to fit inside a worldview built to exclude it. Expecting subjectivity to be explained entirely in terms of objects. Expecting experience to emerge cleanly from equations that never mention it. Quantum mechanics did not introduce consciousness into science. It exposed that consciousness had been quietly ignored. What comes next is uncertain. New experiments may falsify these ideas. Better theories may replace them. Or the mystery may deepen further. But the direction that everything is moving is already clear. We are moving away from a universe where the mind is an accident and towards one where observation, information, and experience are woven into the fabric of what exists. Not as comfort, not as reassurance, but as a reminder that the world is stranger than the stories that we tell ourselves to make it manageable, and that the act of telling those stories is itself part of the phenomenon that we are trying to understand. So, consciousness may not be a passenger in the universe. It may be a mechanism of it. The thing that, at some level, is responsible for reality resolving into something definite at all. That is either the most profound thing physics has ever implied about the human mind, or the most dangerous idea to take seriously before we have the tools to test it properly. But let's hold that question for now, because there is a place where the question becomes impossible to avoid. You spend roughly a third of your life there. Your brain doesn't shut down. If anything, in certain stages it becomes more active. Your sense of self dissolves. Cause and effect stop working the way they do here. Objects transform. Time bends. People appear who don't exist and vanish before you can locate them. And you accept all of it, completely, until you wake up. Dreams are the place where consciousness operates without the scaffolding of the physical world, without sensory input grounding it, and without feedback correcting it. If consciousness has any relationship to the quantum processes that seem to underlie reality, then sleep is the experiment, the test run where all the usual constraints are lifted. Sleep is just death being shy. But what if you never die at all? Every night, something extraordinary happens to you, so familiar that you barely notice it. You climb into bed, close your eyes, and slowly lose contact with the world. The room around you disappears. The concerns that occupied your mind throughout the day dissolve into silence. The identity you spend every waking moment protecting and maintaining fades away. Then, for several hours, you enter a state that remains one of the greatest mysteries in human existence. You dream. Dreams have always fascinated us. Ancient civilizations treated them as messages from the gods. Religious traditions viewed them as portals to deeper truths. Psychologists saw them as windows into the hidden architecture of the mind. Despite centuries of disagreement about what dreams are, one intuition has persisted across cultures and eras. The feeling that dreams are revealing something that we can't normally see. Just as we can't see the inside of a black hole, yet we can observe its effects, and cannot directly observe a quantum system, yet we can learn about it through the traces that it leaves behind, perhaps dreams are traces of something hidden beneath the surface of conscious experience. And in one of the strangest discoveries in modern physics, scientists recently found that a hidden quantum system could reveal itself through something called an echo, which begs the question, what if dreams are doing the same thing? So, in 2024, researchers at Google announced a breakthrough involving a quantum computer known as Willow. The achievement was technical and highly specialized. To learn more about that, watch our video on quantum computing. But buried within it was an idea that feels strangely relevant to the mystery of dreaming. The researchers developed a method known as a quantum echo. Now, to understand what this means, think about how bats navigate in complete darkness. They can't see the cave around them, so instead they emit high-frequency sounds throughout the walls of the cave, and then they listen to the echoes that bounce back. From these echoes, they can build a surprisingly accurate map of their surroundings. And humans, us, we do something similar with sonar. By sending sound waves into the depths of the ocean and measuring what bounces back at us, we can map underwater landscapes or dense rainforest canopies that would otherwise remain invisible. In each case, the principle is the same. When a system is too complex or too dark or too hidden to observe directly, an echo can reveal to us what our eyes can't see. So, the researchers at Google were able to do something similar with quantum computers. A signal is sent through an enormously complex quantum system consisting of more than 100 qubits. During its journey, researchers introduce a tiny disturbance. It's a microscopic change that then spreads through the system. They then reverse the entire process, causing the signal to travel backward. When the returning signal encounters the original one, interference patterns begin to emerge, and these patterns look like an echo. They reveal hidden information about the system's internal structure. By examining the echo, researchers can learn things that would otherwise remain invisible. Now, what makes this idea so fascinating is that it resembles an ancient psychological theory about consciousness. Carl Jung believed that every human being contains a vast unconscious realm that exists beyond ordinary awareness. According to Jung, the conscious mind is only a small island surrounded by an immense ocean of psychological activity. Beneath our awareness lies a world of forgotten memories, suppressed emotions, instinctive drives, archetypal patterns, and latent possibilities. While our conscious mind focuses on the immediate demands of everyday life, the unconscious continues to observe and process and connect information in the background. Jung often spoke about the unconscious as though it possessed its own perspective. It notices things before we do. It recognizes contradictions that we tend to ignore. It detects emotional conflicts that we refuse to acknowledge, but most importantly, it attempts to communicate these insights through its own echoes, and these are dreams. To Jung, dreams are psychological echoes, even though he didn't use those words exactly, but they were sent upwards from the depths of the psyche. They aren't necessarily literal messages, but symbolic ones. The unconscious speaks a different language from the conscious. It communicates through images, metaphors, emotions, and stories rather than direct statements. When you see this, you can understand how it sounds like the echoes that we've been talking about. Just as Google's quantum computer sends a signal into a hidden system and receives information in return, the human mind may descend into sleep and receive signals from regions of itself that are normally inaccessible when you're awake. The dream becomes an interference pattern created by the interaction between conscious awareness and unconscious processes. It is the visible result of an invisible conversation taking place beneath the surface of experience. This idea helps explain why dreams often feel so strange to us. If the unconscious were simply presenting information directly, dreams would look like ordinary waking thoughts. Instead, they arrive wrapped in symbolism, just like the bat doesn't actually see what the inside of the cave looks like, only a representation of it. A dream about a collapsing house may have nothing to do with actual architecture. A dream about being chased may have nothing to do with actual physical danger. The images themselves are often less important than the emotional truths that they represent. The unconscious appears to communicate through symbols because the symbols are capable of expressing layers of meaning that ordinary language just can't. Jung noticed that many of his patients experienced dreams that seemed to understand them better than they understood themselves. People would dream about problems they hadn't consciously recognized. They would encounter symbolic warnings months before a psychological crisis emerged. Sometimes a dream would reveal a hidden fear, an unresolved conflict, or an emotional wound that had remained invisible for years. The dream didn't create the problem. Instead, it exposed something that was already there, just hidden in plain sight. This is what makes dreaming so difficult for us to dismiss. Even if every dream originates entirely within the brain, the question still remains: why is the brain generating them at all? Why devote so much energy to constructing these elaborate symbolic worlds every single night? Why does evolution preserve a process that consumes thousands of hours across a human lifetime if it serves no real purpose? It's then logical to suppose that dreams might serve a purpose far more profound than simple entertainment during sleep. Perhaps they are just part of a navigational system. Just as a bat uses echolocation to move through darkness, the mind may use dreams to navigate regions of itself that can't be directly observed. The unconscious sends signals upward. Consciousness receives them. The resulting dream becomes a map of hidden territory. And if that's true, then every night we participate in a process far stranger than we realize. We assume that sleep is a period of absence, a temporary shutdown of consciousness before waking life resumes. But what if sleep isn't an absence at all? What if it's a journey inwards? What if dreams are the echoes that return from places within ourselves that we rarely encounter during the day? Because if dreams truly are psychological echoes, then every dream carries the possibility of revelation. Every dream may contain information that consciousness has overlooked. Every dream may be evidence that another intelligence exists within us, patiently observing from the darkness and waiting for an opportunity to speak. Most dreams disappear almost immediately after waking. Within minutes, their details begin to dissolve. By lunchtime, only fragments remain. A face without a name, a place that never existed. A feeling that lingers long after the images themselves have vanished. Yet, every so often, a dream behaves differently. Instead of fading, it embeds itself into memory with extraordinary force. Years later, the dream remains as vivid as the day it first happened. Sometimes people remember the colors, the atmosphere, even specific details that would normally be forgotten. More importantly, they often describe the dream as having changed them. Carl Jung became fascinated by these experiences. He called them big dreams. Unlike ordinary dreams, big dreams seem to arrive from deeper layers of the psyche. They possess an unusual emotional gravity. The dreamer often wakes with the unmistakable feeling that something important has happened, even if they can't immediately understand what it means. Jung observed that these dreams frequently appeared during major transitions in life. They emerged before psychological crisis, before profound personal transformations, and before moments when an individual stood at a crossroads without fully realizing it. What makes these dreams so powerful isn't necessarily their content. Sometimes the imagery is surprisingly simple. A person encounters a mysterious stranger, or a bridge collapses. A door opens into an unfamiliar room. On the surface, nothing extraordinary is occurring, and yet, the dream seems to contain more meaning than its images can account for. It feels charged with significance, as though it were carrying information from a deeper source. And this brings us back to the idea of the quantum echo. One of the most fascinating aspects of Google's experiment involved what physicists call a perturbation. Before reversing the signal, researchers introduced a tiny disturbance into the quantum system. The change was almost absurdly small. A single qubit was altered. Yet this microscopic modification propagated throughout the entire system. By examining how the disturbance evolved and interacted with the returning signal, researchers were able to uncover hidden structures that couldn't be observed directly. The entire process depended on something remarkably counterintuitive. A tiny cause leading to a disproportionately large result. In other words, the butterfly effect. Dreams often seem to operate according to a similar principle. A single image in a dream can alter the course of a person's life, just as a butterfly flapping its wings in a rainforest may, through an invisible chain of consequences, change weather patterns on the other side of the planet. The image itself may appear trivial, yet it functions like a psychological perturbation, introducing new information into our consciousness. Once the signal arrives, it begins spreading through the system. The dreamer reflects on it and questions emerge. Assumptions are challenged. Long-ignored feelings begin demanding our attention. What started as a fleeting image gradually transforms into a whole new way of seeing reality. Jung believed that this occurs because dreams reveal patterns that consciousness has failed to recognize. While our waking attention focuses on immediate concerns, the unconscious continuously gathers this information. It notices subtle changes in mood. It tracks recurring emotional conflicts. It detects contradictions between our stated beliefs and our actual behavior. Over time, these observations accumulate into a picture that may be far more complete than the one available to our own conscious awareness. Modern neuroscience actually offers a very interesting parallel. At any given moment, your brain is processing vastly more information than you consciously experience. Most of this activity never enters our direct awareness. Countless signals are filtered out before they reach conscious thought, and yet those signals don't disappear. they continue to influence our behavior from beneath the surface. In fact, actually, experiments have repeatedly suggested that the brain begins moving towards a decision before the conscious mind becomes aware of making one. The feeling of choosing may arrive after the process has already begun. Consciously, it seems, it's often less like the author of our own thoughts and more like a translator, trying to catch up to a story that is already unfolding. So this creates a very intriguing possibility. Perhaps dreams are one of the mechanisms through which hidden information reaches our consciousness. Perhaps they represent moments where the brain attempts to communicate conclusions that it has already reached unconsciously. Consider how often people describe realizing something through a dream that they somehow already knew. The dream isn't necessarily revealing new information to us, but instead it reorganizes existing information into a form that can finally be understood by us. A person dreams about a crumbling building and suddenly recognizes the instability of a relationship. Another dreams about a missing train and realizes they are terrified of wasting their life. The insight feels surprising yet strangely familiar at the same time. The dream acts as an echo, carrying hidden knowledge back to the surface. This idea becomes even more fascinating when we consider reports of dreams that appear to predict future events. And human history is filled with these stories of prophetic dreams. Kings consulted dream interpreters before making political decisions. Military leaders delayed campaigns because of ominous visions had during sleep. Entire religious traditions developed around the belief that dreams could reveal future possibilities to us. Modern people tend to dismiss such accounts as superstition, and yet the phenomenon itself has never fully disappeared. Even today, countless individuals report dreams that seem uncannily predictive. They dream about conversations before they happen. They dream about accidents, illnesses, or unexpected encounters that later happen in real life. Now, most of these stories can be explained through coincidence, or selective memory, or the tendency to reinterpret events after the fact. Human beings are excellent pattern-seeking creatures, and we often connect unrelated events into meaningful narratives. And yet, there may be another explanation that isn't mystical as dreams predicting the future, but perhaps even more interesting. Imagine that the unconscious mind is constantly analyzing information before conscious awareness. It notices subtle tensions in a relationship long before you realize the toxicity. It detects signs of physical illness before symptoms become obvious. It recognizes patterns in behavior that point towards future outcomes. If a dream emerges from this deeper level of analysis, it may appear prophetic without requiring any supernatural mechanisms. The unconscious may simply be better at prediction than our consciousness. A skilled chess player can often sense the direction of a game several moves in advance, even without actively having to think about it. If you were to ask them, they maybe wouldn't necessarily be able to explain how they know, but years of pattern recognition allows them to anticipate future possibilities. Perhaps the unconscious functions in a similar way. It models reality, generating predictions based on information that never reaches conscious awareness. If this is true, then the dream isn't showing us the future, it's showing us a future. One possible trajectory among many, an echo of where our current path may lead. Jung found this possibility deeply compelling because it transformed dreams from passive experiences into active guides. The dream was no longer a reflection of the past, it became a tool for navigating the present and a vision for the future. And this may explain why certain dreams feel less like memories and more like messages. The dream isn't merely replaying information to us, it's reorganizing it into a form that consciousness can understand. And sometimes the signal is so powerful that it becomes impossible to ignore. But if we agree that dreams are echoes, then the next logical question becomes, what is the source of the echo itself? And this is where things start to get a lot stranger. Because eventually we arrive at a mystery that has troubled philosophers, mystics, and psychologists for centuries. A mystery hidden inside the simplest question imaginable. What exactly happens to consciousness when we fall asleep? At first, the question sounds simple. We assume we already know the answer. The brain enters different stages of activity, dreams emerge and disappear, and then we wake up. But the more closely we examine the experience of sleep, the stranger it becomes. Consider what happens every single night. You lie down in bed, you close your eyes, and gradually you lose awareness of the world. The room disappears, sounds fade into the background, and thoughts become fragmented. Then at some point, your consciousness itself seems to vanish. Hours pass, and yet from your perspective, no time has passed at all. This is one of the most overlooked mysteries in human existence. We spend nearly a third of our lives asleep, but we rarely stop to consider what that actually means. During waking life, experience unfolds continuously. One moment leads to another. There's a sense of duration, of movement, and persistence. Even when we're bored, the consciousness remains present. But dreamless sleep appears different. There's no through line, no story, no memory, no awareness of passing time. One moment, you are falling asleep, and the next you are waking up. Between these 2 points lies an apparent void, a gap in existence. The philosopher Schopenhauer once compared sleep to a temporary return to the state that existed before birth. More modern thinkers have described it as a kind of nightly death, an interruption in the stream of conscious experience so complete that it raises uncomfortable questions about personal identity itself. After all, if consciousness completely disappears each night, what exactly returns in the morning? Well, the answer seems obvious. You return. But when examined carefully, the certainty begins to weaken. The self feels continuous because memory creates continuity. You remember who you are. You remember yesterday. You remember falling asleep. Those memories create the impression of an uninterrupted existence, and yet the actual experience of dreamless sleep remains inaccessible. Consciousness seems to vanish entirely. Some traditions have embraced this mystery rather than avoiding it. In ancient Greece, sleep and death were represented as twin brothers. Across many cultures, sleep was understood as a temporary journey into the unknown, a brief departure from ordinary reality. Even today, there is something unsettling about surrendering our consciousness. Every night we willingly allow the most intimate aspects of our existence to dissolve into darkness. The philosopher Thomas Nagel once asked what it was like to be a bat. His point was that conscious experience possesses a subjective quality that can't be fully explained from the outside. We know what it feels like to be ourselves because we experience it directly. But what does it feel like to be unconscious? The question can't be answered because there is no one there to answer it. Dreaming at least provides content. Dreams are experiences. However strange they may be, there is still a world being perceived. Dreamless sleep offers something entirely different. It appears to be the absence of a world altogether. And yet consciousness somehow returns at the end of it all. Each morning, awareness reassembles itself. The universe comes back online. The familiar narrative of I resumes exactly where it left off. Why? What determines that consciousness returns at all? Most scientific explanations focus on brain activity. Certain neural networks deactivate while others remain active. Various regions coordinate the transition between wakefulness and sleep, and these explanations are valuable, but they leave a deeper philosophical question unanswered. Why does subjective experience emerge from this process in the first place? Why is there something like consciousness? And where does that something go when consciousness disappears? Carl Jung approached this mystery from a very unique angle. Late in life, Jung recorded one of the strangest dreams of his career. Unlike many of his other dreams, this one seemed to challenge his understanding of identity itself. In the dream, Jung found himself standing inside of a temple. There, seated in deep meditation, was a yogi. The figure appeared ancient, serene, and completely absorbed in contemplation. As Jung observed the meditator, he gradually noticed something troubling. The yogi had Jung's face. The realization struck him with immense force. At first, Jung assumed he was observing another version of himself. Then a more disturbing possibility emerged. What if the relationship was reversed? What if the yogi was not being dreamed by Jung? What if Jung was being dreamed by the yogi? The dream produced an overwhelming insight. The meditating figure seemed to exist at a deeper level of reality than the conscious personality that Jung identified with. The ordinary Jung, the man moving through daily life, suddenly felt like a secondary character, almost fictional. He sensed that if the yogi were ever to awaken, Jung himself would disappear. That dream haunted him for years, because beneath its bizarre imagery lies a profound philosophical question. What if the conscious self is not the deepest layer of identity? What if the person that you think you are exists only at the surface? Modern psychology often describes consciousness as a small fraction of mental activity. Most cognitive processes occur outside of awareness. Decisions begin unconsciously before they enter consciousness. Emotions emerge from systems that we can't directly control. Perceptions are constructed by mechanisms operating beyond our awareness. Like I said earlier, the conscious self may be less like a ruler and more like a translator. Jung's dream takes this idea to its logical extreme. Imagine that your waking identity is only the visible portion of a much larger process. Imagine that beneath your everyday awareness exists a deeper intelligence, one so vast that your conscious personality represents only a temporary expression of it. In that case, falling asleep wouldn't mean consciousness disappears, it would mean consciousness retreats from one level of reality to another. The dreamer would become the dreamed. The observer would become the observed. The self would discover that it is part of something larger than itself. This possibility appears repeatedly through human history. Mystics describe awakening from the illusion of individuality. Eastern philosophies speak of the ego as a temporary construction rather than an ultimate reality. Certain religious traditions portray ordinary consciousness as a dream from which deeper awareness eventually emerges. Of course, none of this proves that such ideas are true, but their similarity across cultures with no interaction to one another is striking. Across different cultures, centuries, and belief systems, people repeatedly arrive at the same intuition. The feeling that the self we experience every day may not be the deepest level of the self that exists. Perhaps this is why sleep feels so mysterious. Every night we are approaching a boundary. On one side lies the familiar world of waking consciousness. On the other lies a territory that we barely understand. Dreams emerge from that territory, carrying symbols, warnings, insights, and strange fragments of meaning. Yet beyond the dreams themselves lies something even more elusive, the darkness from which they emerge. And if dreams are echoes, then perhaps the most important question isn't what the echoes mean to us. Perhaps the real question is what's creating them. Anyone who has experienced a vivid dream knows how convincing they can be. While the dream is happening, it rarely feels imaginary. The dream world possesses its own internal logic, its own physics, and its own sense of reality. We accept impossible events without question. We speak to people who have been dead for years or who have never existed. We visit places that don't exist. We watch entire narratives unfold. Yet throughout the experience, everything feels perfectly normal to us. It's only after waking that we recognize how strange it all was. And this creates an interesting problem. How do you know you're awake right now? Well, at first, the answer seems obvious. Pinch yourself. Reality feels stable. The laws of physics behave consistently. Memory connects one moment to the next. Unlike dreams, our waking life appears coherent. But dreams often feel coherent while we are inside them. In fact, one of the more troubling experiences a person can have is what psychologists call a false awakening. The dreamer wakes up inside a dream, and everything appears normal. You are back inside your bedroom, and your bedroom looks correct. So your morning routine begins. Reality seems perfectly intact. Then something impossible happens. The dreamer realizes they are still asleep. Sometimes this process repeats multiple times. A person wakes up only to discover that they are dreaming. Then they wake up again and again. Each layer feels more convincing than the last. These experiences are often called nesting dreams. People who have undergone them frequently describe a profound sense of disorientation afterwards. For a brief period, the boundary between dream and reality feels uncertain. If the previous layer felt real while it was happening, what guarantees that the current layer is any different? Well, philosophers have been haunted by this question for centuries. In the 17th century, René Descartes famously wondered whether any experience could prove with certainty that he was awake. Every test he devised encountered the same problem. Dreams could imitate nearly everything he experienced during waking life. If a dream can reproduce sight and sound, touch, memory, emotion, and narrative continuity, then what criterion remains for distinguishing one state from the other? The question remains surprisingly difficult to answer. Most of us rely on practical certainty. We assume we're awake because reality behaves consistently over time. And yet, from a purely subjective perspective, consciousness experiences both states directly. The dream feels real while it lasts. Waking life feels real while it lasts. This is where the metaphor of the quantum echo becomes particularly interesting. One way to think of dreams is as a simulation. Modern neuroscience increasingly suggests that the brain functions as a prediction engine. Rather than passively observing reality, it continuously generates models of the world and updates them using incoming information. In a sense, the brain is always simulating reality. Perception itself may be partly constructed from internal predictions. Dreaming appears to take this tendency even further. During sleep, external sensory input decreases dramatically. The brain becomes free to generate entire worlds from within. It creates environments, characters, conflicts, and whole scenarios. It runs simulations. Many researchers believe this serves an adaptive purpose. Dreams may help us rehearse threats. They may allow us to explore social situations in a safe environment. They may help consolidate memories, process emotions, and prepare for future challenges. In this view, dreaming is less like watching a movie and more like playing the training area in a video game. The sleeping mind generates possibilities and examines their consequences. It experiments, it explores, and it asks questions. What happens to us if this relationship ends? Or what happens to me if I fail to reach my goal? Or what happens if my biggest fear becomes true? The dream becomes a laboratory for consciousness. But then, many people also report experiences that feel far longer than the actual duration of the dream. Some describe living through years of subjective experience. Others report entire alternative lives complete with relationships, histories, and their own memories. When they wake, the emotional impact can be overwhelming. There are accounts of people mourning dream families that never existed. Others struggle to reconcile memories from dreams with memories from waking life. For a brief period, both seem equally real. Such experiences reveal something remarkable about consciousness. Reality isn't simply something we observe. Reality is something that we construct. The world you experience is always filtered through the brain's interpretation of information. Dreams demonstrate just how powerful that interpretive process can become. Given the right conditions, the mind can create worlds capable of rivaling reality. And this raises such a provocative possibility. What if waking consciousness itself is only one level within a larger hierarchy? After all, every dream feels real until a higher level of awareness appears. The dreamer wakes and suddenly recognizes the dream for what it was. The previous reality is revealed as a construction nestled within a broader reality. But what if the process doesn't stop? What if waking consciousness is simply another layer? This idea appears in countless philosophical and spiritual traditions. Plato imagined an ordinary reality as shadows projected onto a cave wall. Hindu philosophy describes the world as Maya, a veil of appearances. Mystics throughout history have spoken of awakening from ordinary consciousness into a more fundamental reality. Again, these traditions differ enormously in their details, yet they often converge on a similar intuition, that the reality that we take for granted may not be the deepest reality available to us. Dreams provide a glimpse of how such a thing could be possible. Every night, consciousness effortlessly generates convincing worlds. Every morning, it abandons them and moves into another. The transition feels natural because we have experienced it thousands of times. But perhaps we have become too accustomed to the miracle. Perhaps the truly astonishing fact is not that dreams feel real. Perhaps the astonishing fact is that reality itself feels real. The same consciousness that constructs dream worlds is the consciousness through which you experience everything else. The same mind capable of creating entire universes during sleep is the mind through which your waking world appears. And if dreams are echoes emerging from deeper layers of the psyche, then maybe they serve another purpose as well. Maybe they remind us that reality is more fragile, more mysterious, and more dependent upon consciousness than we usually imagine. Because once you realize that entire worlds can emerge from the mind, another question becomes impossible to ignore. If dreams can alter our experience of space and reality, what about our experience of time? There's one final aspect of the quantum echo that makes it such a powerful metaphor for dreaming. The output of Google's experiment is something physicists call an out-of-time ordered correlator, or OTOC. Despite the intimidating name, the basic idea is surprisingly simple. An OTOC measures how information spreads through a complex system over time. It reveals how different parts of the system influence one another across both space and time, exposing relationships that would otherwise remain hidden. In other words, the quantum echo is not merely telling researchers what a system looks like. It is revealing how events separated in time are connected. For a physicist, this is a technical tool. For anyone interested in dreams, it is an irresistible metaphor, because one of the strangest features of dreaming is its relationship with time. Dreams seem to obey entirely different temporal rules from waking life. Hours can pass in seconds. Entire narratives can unfold within moments. Past experiences merge with imagined futures. Events separated by decades appear side by side as though they're occurring simultaneously. The ordinary flow of time becomes fluid, almost irrelevant. Many people have experienced dreams that they feel as though they exist outside chronology altogether. Childhood memories blend seamlessly with present concerns. Future anxieties appear as symbolic landscapes. Long-dead relatives speak about events that have not yet happened. The dream mind moves through time the way a person might move through rooms in a house in a non-linear fashion. This is one reason dreams have always seemed prophetic to us. What matters isn't whether every claim is true. What matters is that the experience itself feels profoundly convincing to those who are experiencing it. The dream creates the impression that consciousness has briefly escaped the normal flow of time. Carl Jung became fascinated by this possibility. While he remained cautious about supernatural explanations, he also recognized that human experience sometimes contains coincidences so meaningful that they become rather difficult to easily resist. He referred to these events as synchronicities. They weren't necessarily examples of mystical causation. Instead, they seemed to be examples of connection. Inner experiences and outer events aligning in ways that felt deeply significant. Dreams often occupy the center of these stories. A person dreams of an old friend and unexpectedly encounters them the next day. Someone dreams of a major life transition shortly before it actually arrives. A symbolic image appears repeatedly until an event finally gives it meaning. Whether these experiences represent unconscious prediction or something stranger, they produce the same feeling. The sense that consciousness may perceive patterns extending beyond the present moment. Perhaps this is because the unconscious experiences time differently. Your conscious mind lives almost entirely in the present from moment to moment. It focuses on immediate tasks, or immediate threats, or immediate goals. The unconscious operates on a broader scale. It integrates years of memories, emotional associations, and behavioral patterns. It continuously models possible futures based on available information. From this perspective, the unconscious resembles an extraordinarily sophisticated predictive engine. It is constantly asking questions. Where is this relationship heading? What happens to me if these habits continue? What future emerges from the choices that are being made today? And the answers to those questions arrive as dreams. An experienced sailor often predicts a storm hours before it arrives. The prediction doesn't require supernatural knowledge. It emerges from sensitivity to subtle patterns invisible to inexperienced voyagers. Perhaps dreams function similarly. Perhaps what feels like prophecy is just really good pattern recognition operating beneath awareness. Yet, even this explanation leaves some mystery behind. Why does the unconscious communicate to us through stories? Why dreams? Why not simply present these conclusions directly? The answer may lie in the nature of consciousness itself. Facts can change behavior less effectively than experiences can. A person can intellectually understand a problem for years without taking action. A powerful dream can communicate the same truth in a single night. And let's be honest, facts do not change people's minds. Feelings do. Dreams are a powerful way to shape those feelings. The dream succeeds because it doesn't merely tell us something. It's allowing us to experience something. And this brings us back to the central idea of the quantum echo. So let's go back to a bat flying through a cave. The bat can't see the darkness directly. It can't observe every wall or every tunnel or every obstacle. Instead, it is sending signals outward and listening carefully to what comes back to it. The echoes then create a map. The invisible then becomes visible. The unknown becomes navigable. Perhaps dreams serve a similar function. The human psyche is too vast to fully comprehend. Beneath conscious awareness lies an immense landscape of memories, instincts, fears, desires, archetypes, and possibilities. We can't directly observe most of it. We can't walk through it the way we would walk through a city. It remains hidden from us in darkness. So, the mind sends a signal into itself. Dreams are what come back to us. They're echoes generated by the interaction between conscious awareness and unconscious depths. They reveal hidden structures. They expose emotional truths. They forecast possible futures. They guide adaptation and growth. Sometimes they warn. Sometimes they comfort. Sometimes they confront us with realities that we would rather avoid. But they always remind us of the same thing. We are larger than we appear. The conscious self feels like the center of identity, and yet it may be only the surface of a much deeper process. Every night, that deeper process becomes visible for a few brief hours. Images emerge from darkness. Stories rise from hidden regions in the mind. Signals travel upward from places we rarely encounter during the day. But then, morning arrives. The dream dissolves. The ordinary world returns to us. Emails need answering. Conversations need to be had. Life resumes its familiar rhythm. Yet somewhere beneath that routine, the deeper mind is continuing its work. It continues observing. It continues connecting. It continues to generate echoes. And tonight, when you fall asleep, the process will begin again. Your conscious world will fade. The darkness will return. And from somewhere beyond the boundaries of ordinary awareness, another signal will start its journey back towards the surface. The question is whether you're going to listen. Because if dreams are quantum echoes of the soul, then sleep is not an escape from reality. It's a conversation within the hidden parts of ourselves that reality often keeps silent. And every dream is an answer to a question we didn't know that we were asking. We've only just scratched the surface of the research that discovered the concept of quantum echoes. So, consciousness persists through sleep, through the dissolution of the self, through the complete removal of sensory reality. It reconstructs itself every morning from whatever process is running underneath, and then it calls itself you. Now, take the many worlds interpretation. You've encountered it in pieces throughout this marathon. The idea that the wave function doesn't collapse into one outcome, it branches. Every possible outcome happens in diverging versions of reality. There's a version of you that made every decision that you have made throughout your entire lifetime differently. A version that left. A version that stayed. A version that took a different road. And these branches don't communicate with each other. You can't feel them. But according to the physics, they are as real as this one. If every possible outcome always happens somewhere, what does survival mean? Because in every branch where you could survive, you do. There's always a version of you that made it through. The branches where you don't survive are simply the ones your consciousness is no longer present to experience. You can't observe your own absence. By definition, every version of you that can ask the question, am I alive, is still alive. So let's follow that logic to its conclusion. And it doesn't lead us anywhere comfortable. It leads to quantum immortality. The idea that from the inside, from the only perspective you will ever have, you can't die. And that is either the most beautiful thing the universe has accidentally implied about existence, or the most terrifying. Quantum immortality. It's one of those ideas that sounds ridiculous when you first hear it. In essence, it suggests that from your own point of view, you may never be able to experience your own death. In simple terms, if the universe splits into multiple possible outcomes, then there will always be some version of reality in which you survive. And if your consciousness can only ever continue in branches where you're still alive, then subjectively, you would never reach a moment where everything just ends. At first, all of this sounds ridiculous, like pure science fiction, a story about endless parallel worlds, alternate versions of you, and some strange loophole in death itself. But people still take the idea seriously, not because it offers a comforting promise of eternal life, but because it grows out of a real problem at the heart of modern physics. A place where our best theory of reality stops feeling like a clean explanation and starts feeling like an argument against common sense. Quantum immortality is not disturbing because it says you might live forever. It's disturbing because it asks a more corrosive question. If reality never chooses a single outcome, then why do you experience a single life at all? To understand why that question is so unsettling, we have to start with the part of quantum mechanics that physicists have spent nearly a century trying to explain without ever fully resolving. At the quantum level, particles do not behave like tiny solid objects following clean, deterministic paths through space. They're described by something called a wave function, a mathematical structure that encodes multiple possible states at once. In simple terms, a particle can exist in what is known as a superposition, meaning not simply here or there, but in a distribution of possible outcomes that only becomes definite when the particle is observed. And yet, when we look at the world, we don't encounter blurred clouds of possibility. We encounter single events. There's a particle here, the door is there, there's a window over there. It's one reading, one outcome instead of all of them at once. Somewhere between mathematics and the world as it appears, infinite possibilities seem to harden into singular fact. That's the measurement problem. And it's not some minor technical issue hidden in the machinery. It is the point where the most accurate theory in the history of science becomes strangely silent about what reality is actually doing. For decades, the most widely taught response to this problem was the Copenhagen interpretation. In its broadest form, it says that the wave function evolves as a spread of possibilities until an observation or measurement takes place, at which point it collapses into one actual state. Before observation, multiple outcomes remain alive within the formalism. After observation, only one remains real to us. This story is neat, it's teachable, and most importantly, it appears to match experience. But inside that apparent simplicity is a deep and unresolved instability. The mathematics themselves do not clearly specify what counts as a measurement. It doesn't tell us exactly where the line sits between the quantum system and the classical observer. It doesn't explain why a detector should count as sufficient, or whether a conscious mind is somehow necessary, or when precisely a possibility becomes an event. The theory predicts astonishingly well, but the explanation attached to it has always felt questionable. In 1957, Hugh Everett III proposed an answer that was radical precisely because it refused to add anything new. Instead of modifying the equations, he took them more seriously than anyone else wanted to. His suggestion was simple in form, but devastating in its implication. The wave function doesn't collapse. Ever. The equations of quantum mechanics already describe reality completely, and if those equations continue evolving into multiple outcomes, then perhaps the mistake is not in the mathematics. Perhaps the mistake is in our refusal to believe that all of those outcomes are real and that they exist. This became known as the many worlds interpretation. Under this view, every possible result of a quantum event actually occurs. Reality doesn't narrow into one history. It branches out into many. The universe doesn't choose one path and erase the rest. It unfolds into a vast structure of parallel, non-interacting branches, each containing one outcome that appears singular from the inside. What looked like collapse was only a limitation of our understanding. If many worlds is true, then the reality you take for granted is not the structure itself. It's only your local position inside of it. Every quantum event becomes a fork. Every unresolved possibility, a divergence. There's a branch where the particle decays and a branch where it doesn't. A branch where the detector clicks and a branch where it remains silent. A branch where events unfold in the way that you remember, and a branch where they don't. At the level of ordinary experience, these branches become isolated from one another through a process called decoherence, which is why the world still feels stable and classical from within. You don't meet your alternate selves in the hallway. You don't watch possibilities shimmer in front of you like overlapping transparencies. The branching isn't dramatic in the way that fiction imagines it. It's much, much more quiet than that, more mechanical and yet more absolute. And this is the point where the theory stops sounding abstract and starts becoming a lot more personal. Because once you accept that every outcome happens somewhere, a disturbing asymmetry emerges between the world as described from the outside and the world as experienced from the inside. And hidden inside that asymmetry is the seed of quantum immortality. To make the idea of quantum immortality easier to understand, philosophers and physicists created a thought experiment called quantum suicide. The setup is simple. Imagine a device connected to a quantum event with two possible outcomes. If the event resolves as option A, the device fires and takes you out instantly, you're gone. If it results as option B, congratulations. Nothing happens, you have continuity. Each time the experiment runs, your fate is directly tied to a random quantum result. Under an ordinary single-world view of reality, this is just a deadly gamble, far worse than Russian roulette, with every roll of the dice giving you a 50-50 chance of proving your mortality. However, under the many worlds interpretation, the situation changes completely. The quantum event does not produce one final outcome that replaces all of the others. Instead, it causes reality to branch out into these different outcomes. In one branch, the device fires. Sorry, you're done. In another, it doesn't. Hooray. Both outcomes happen, but in different branches of the universe. From the outside, both branches are equally real. There are worlds in which the experiment ends with your death and worlds in which you survive to hear the click. But from your own point of view, you always survive, since you can only ever be conscious in the branches where you are still alive to experience anything at all. The branches in which you die are still very real, but because they contain no continuing awareness, there's no observer left behind to register the result. If every lethal quantum event creates at least one branch in which you survive, and if your consciousness can only ever continue along the branches where it remains conscious, then subjectively you would never experience the moment of your own death. From the outside, death still happens. In fact, it happens often. But from the inside, awareness seems to keep finding itself in the branch where the story hasn't ended yet. Other people still lose you. Bodies will still fall. Tragedy strikes. But your own perspective appears to be dragged again and again into the improbable branch where the story continues. And this is what turns quantum immortality from a comforting idea about eternal life into something a lot darker. This is the first major distortion people miss when they hear the phrase. They imagine immortality as indefinite youth, or at least indefinite coherence. A body with a unified consciousness that goes on functioning forever. But the logic of the theory doesn't care about comfort, dignity, health, or even your own identity. It only cares, if that is frankly even the right word, that some strand of awareness remains available, just enough consciousness to preserve a point of view, an observer, just enough neural function for experience not to collapse entirely into nothing. And that threshold, as it turns out, may be horrifyingly low. You don't need to be whole as a person to count as continuous. You don't even need to be well physically or mentally. You may only need to still be there. And that's where the fantasy curdles. Because once survival is stripped of its wholeness, it stops looking like a gift and starts looking like an everlasting prison cell. This is why some philosophers describe the end point not as immortality, but as a kind of ghostliness. Not supernatural in the way that we often think of it, but probabilistic ghostliness. A condition in which your existence becomes mathematically marginal, suspended in the far outskirts of what should still be happening. If the body deteriorates, then consciousness may not continue as a clear, uninterrupted stream. It could fragment, it might stutter, it might even thin into discontinuous flashes. Brief windows of awareness opening inside longer fields of confusion, pain, sedation, amnesia, or neurological ruin. Perhaps what persists is not a stable self moving cleanly through time, but a sequence of degraded moments, each barely sufficient enough to count as a continued observation. Not a life, but intermittent residue. Not eternity in the grand mythic sense, but eternity reduced to broken frames. A mind that cannot fully die, but can no longer fully live either. If that sounds less like immortality and more like a hellish punishment, that is because the theory doesn't distinguish between the two. It only distinguishes between awareness and the absence of awareness. Everything else is just collateral. There is also the problem of isolation, and this may be the cruelest consequence of them all. Because even if your consciousness continues, everyone else still lives inside branches where you don't. Your family mourns you. Your friends miss you. The world recognizes your absence and then reorganizes itself without you. In the surviving branches, they may still be present for a while. But as time passes, ordinary mortality continues its work on them too. They age, they weaken, they disappear. The people you love don't become immortal just because your awareness keeps slipping forward into narrower possibilities. So the longer the process lasts, the more separated you become from the human world that once gave your survival meaning. And this here is the hidden reversal at the center of the whole idea. We fear death because we assume the opposite of death is life. But quantum immortality suggests the opposite of death may simply be more experience. And those are not the same thing as life. A theory that cannot distinguish vitality from persistence ends up exposing something we usually try not to think about. What we actually want is not an endlessly long life. It's a meaningful continuity of our present conscious experience. It's wholeness. It's a self that remains capable of living rather than merely existing. Once you strip that away and you clearly see that immortality is a punishment because it completely strips life of whatever meaning and beauty it holds. There's another problem buried inside quantum immortality, and it cuts deeper than the fear of an endless, damaged survival. Even if we grant the full logic of many worlds, even if we assume consciousness always continues along some surviving branch, it still doesn't mean that the thing continuing is meaningfully you. This is where the theory collides with a question older than quantum mechanics and more destabilizing than death itself. What exactly is the self that persists from one moment to the next? We talk as if identity was obvious, as if the person who wakes up tomorrow is simply the same person who fell asleep tonight. But that confidence rests on something surprisingly fragile. Memory, bodily continuity, psychological coherence, narrative stability, these are the threads from which the ordinary self is woven. And none of them are as absolute as they feel, at least not in any measurable way. In everyday life, we ignore that fragility because change happens slowly enough to preserve the illusion of a single, uninterrupted identity. You age, but gradually. You forget, but selectively. Your body renews itself cell by cell. Your beliefs shift and your values mutate, your memories distort, and still you continue referring to the result as the same person. The continuity feels real because the transitions are smooth. But identity may be less like a solid object and more like a pattern that keeps reasserting itself across time. And patterns can degrade and they can split. They can drift so far from their origin that the name remains while the structure underneath becomes almost unrecognizable. If that's already true in ordinary life, then quantum branching completely shatters that illusion that there ever was one stable you to survive in the first place. Under many worlds, every branching event creates multiple future versions of the observer. These versions share a common past up to the moment of divergence, but after that, they begin to accumulate different experiences, conditions, and outcomes. At first, the difference might be microscopic. In one branch, a particle decays. In another, it doesn't. But over time, these small divergences compound into radically distinct lives, different injuries, different environments, different memories, different endings. So the question is then, which one is you? All of them inherit your past. All of them can legitimately say they came from the same earlier observer, but they can't all be numerically identical in the ordinary sense, because they become distinct centers of experience. Identity, under branching, becomes distributive. The self doesn't continue as one line, it proliferates into many different descendants. That matters, because quantum immortality quietly relies on a trick of language. It says that you will always find yourself in the branch where you survive. But that sentence only feels intuitive because the word you is doing way too much work. Which you? The present observer imagining the future? The future branch that retains enough continuity to feel like a successor? The set of all descendants with some claim to your history? Once branching becomes real, identity no longer behaves like a single thread pulled intact through time. It behaves more like a tree. And a tree doesn't have one future, it has many. Some branches flourish, some terminate, some twist into distorted forms that still emerge from the same trunk but no longer resemble the shape that you expected. The theory doesn't guarantee your personal immortality. It may only guarantee that among your many descendants, some conscious remnant continues. That is a much colder statement, in my opinion. To see why, imagine a less dramatic version of the problem. Suppose tomorrow your brain were altered in a way that preserved some memories and some traits, but fundamentally changed your emotional life, your values, your perception, and your capacity for reflection. The resulting person might still answer to your name, they might still recognize your loved ones, and they might still carry fragments of your history. But would you regard that being as straightforwardly identical to yourself? Or would you feel that something more essential had been broken, even if the biology was still working? We already recognize in cases of severe brain injury or degenerative illness that there's a difference between an organism surviving and a self remaining intact. Oh sure, the body continues, awareness continues, but continuity in the richer personal sense becomes uncertain. Quantum immortality tends to glide past that distinction. It treats any surviving awareness as sufficient. But a consciousness that merely emerges from your prior state is not necessarily the same as the person in that prior state. This is where the concept starts to resemble teletransportation thought experiments and other philosophical puzzles about personal identity. If a perfect copy of you were created elsewhere with all your memories up to this instant, would you wake up as that copy? Or would the copy simply believe it was you, while your own consciousness remained tied to the original body? There's no consensus on this, because the problem exposes a deeper instability in how we think about selfhood. We treat first-person continuity as a primitive fact, but under analysis it becomes difficult to locate. Is identity a matter of physical continuity, a psychological resemblance, causal connection, informational pattern, or, hey, is it something else entirely? Quantum immortality leans heavily on the idea that first-person continuity will always follow survival. But unless identity is far simpler than it appears, that assumption is doing much more philosophical work than the physics itself. And the darker possibility is that the theory only preserves a kind of successor bias. In every branching event, there will always be some future observer who remembers being you. That observer will naturally interpret their own existence as a continuation, because memory presents itself from the inside as inheritance. But memory isn't proof of identity. It's evidence of causal descent. A copy with your memories would also feel like a continuation from the inside. So would a damaged successor, assembled from enough surviving fragments of your former mind. The fact that some future awareness claims your past doesn't settle whether your present consciousness truly becomes that awareness. It only shows that a later observer carries your imprint. Quantum immortality, in that sense, may not protect the self. It may only guarantee the production of survivors who insist they are its rightful continuation. And I get it. That sounds abstract until you confront what it means emotionally. The fear hidden inside death is that the unique center from which experience is happening ends. The one reading these words, the one carrying this exact perspective, this exact structure of memory and feeling, this exact sense of I. If quantum immortality merely says that some future observer with enough resemblance continues in a surviving branch, then it hasn't necessarily defeated that fear. The singular center you care about may still disappear, replaced by successors who feel close enough to claim the inheritance without being strictly identical to the original. In that case, the promise of subjective immortality begins to thin out. What survives isn't necessarily the self after all, it may just be its aftermath. And yet, this doesn't fully dissolve the horror, it just changes it. Because the theory no longer threatens you with endless life as a stable person, it threatens you with indefinite fragmentation of your personhood. And that may be the most destabilizing implication yet. Because quantum immortality only sounds coherent if you already believe the self is a simple thing, a single bead carried forward on the wire of time. But the closer that you examine consciousness, memory, and branching identity, the more that image begins to fail. The self may not be a bead, it may only be a temporary knot, a local organization of matter and memory that holds for a while, then loosens, divides, and disappears into descendants that resemble it without preserving it perfectly. If that's true, then the real horror is that death may not arrive as a clean ending. It may be replaced by a long, splintering recession in which the self becomes less singular, less coherent, less certain of its own claim to be the thing that began the journey. Instead of one clean black screen, bang, you're done, you just live forever in an endless ocean of gray. Up to this point, quantum immortality has felt like a nightmare because it follows its own logic so cleanly. But this is also the point where the idea runs into its hardest resistance, from the structure of consciousness itself, from the biology of dying, and from the fact that the theory quietly assumes more than the physics ever actually gives it. Quantum immortality feels powerful because it borrows the authority of quantum mechanics. The problem is that it may be borrowing a bit too much. The first crack appears in the simplest place. The theory assumes that consciousness behaves like a single invisible thread, something that can continue smoothly from one branch of reality into another, so long as a surviving observer remains. But neuroscience doesn't describe the mind in that way. It doesn't reveal one unified witness sitting behind the eyes, waiting to be routed down the correct timeline. It reveals a distributed, fragile, highly physical process emerging from the coordinated activity of billions of neurons. You damage those neurons and the personality changes. Damage them differently and memory changes them. Damage them again and the continuity of self begins to fail. The mind doesn't look like a detachable essence from that point of view. It looks like a biological event. And if consciousness is inseparable from the physical substrate of the brain, then the language of jumping to a surviving branch stops making any sense biologically. This matters because the seductive version of quantum immortality depends on a categorical mistake. It takes the essence of another surviving brain in another branch and quietly treats that as a continuation of your present awareness. But those aren't the same claim. At most, many worlds gives you a duplication. It gives you parallel descendants emerging from a shared prior state. It does not, by itself, supply a mechanism by which first-person consciousness transfers from a dying brain here to a surviving brain there. That extra step is the entire horror and the entire premise of the idea, and it's precisely that step that the physics never proves. The deeper you follow this, the worse it gets for the theory. Because even if you ignore the substrate problem, even if you pretend consciousness is unified enough to be considered as a single stream, biology still refuses to cooperate. Quantum suicide thought experiments are clean because they rely on instantaneous, binary outcomes. The gun fires, or it doesn't. A clear dividing line appears between awareness and oblivion. But that's not how most real death happens, as I'm sure you're aware. Most deaths are a process of progressive failure. There's oxygen loss, then cellular damage, neural breakdown, inflammation, disorientation, sedation, delirium, coma, dead. Consciousness doesn't always vanish in a single clean cut. It often thins, fragments, and then decays. And once death becomes gradual, the whole machinery of quantum immortality begins to lose its grip. Because where, exactly in that slow biological collapse, is the branching supposed to save you? At what moment does subjective awareness decide, I'm not going to dim here, but I'm actually going to move over there? Does it happen when our memory is failing? When cortical activity becomes erratic? When identity is already breaking apart under chemical and structural damage? Well, the theory offers no answer, because the answer would require more than quantum mechanics. It would require a precise accounting of what consciousness is, where it begins, where it ends, and how much of it must remain for a future observer to count as a continuation of the present one. And science doesn't currently have that account. Quantum immortality behaves as though it does. It treats the most mysterious feature of existence, first-person awareness, as though it were an obvious rule. And if you haven't cottoned on to this yet, it isn't an obvious rule. It is the very thing that we don't understand. Then there's the problem of probability. The many worlds interpretation says that all possible outcomes occur across branching universes. But if everything happens, what exactly does it mean to say you are likely to experience one thing rather than another? In ordinary life, probability tells us how often outcomes occur. In many worlds, every outcome with non-zero amplitude occurs somewhere. So the theory of subjective certainty begins to rely on a very strange maneuver. It says that branches in which you die should be discarded from your first-person accounting because no conscious observer remains there to register the result. But critics argue that this is not licensed by the mathematics. There's no equation in quantum mechanics saying that awareness must automatically privilege the surviving branch while ignoring the dead ones. That conclusion feels intuitive only because death contains no witnesses. But the absence of evidence is not the evidence of absence. My dad loves that saying. That distinction is devastating, because once you remove the emotional pull of, I can only experience being alive, what remains is much thinner than people expect. Of course, you cannot observe your own non-existence. Nothing can. But that doesn't imply that the next surviving observer elsewhere in the branching structure is guaranteed to be you in the strict first-person sense that matters to us. As if it's not bad enough, there is also a final problem, and it's colder than the others because it doesn't attack the theory's logic. It attacks its status as science. A scientific idea must, at least in principle, be capable of being wrong. There must be some possible observation that would count against it. Quantum immortality slips away from that requirement from the outside. It's invisible. Other people just watch you die. From the inside, it's self-confirming. Any close call can be reinterpreted as evidence that your consciousness remained in a surviving branch. The theory cannot be cleanly verified because only the survivor can claim the evidence, and it can't be cleanly falsified because the dead do not report back their experience. If you have an alternate experience, please tell me, because I need to know. A system that turns every possible experience into apparent support is never science. And this is why most physicists reject the idea. And even many of those willing to entertain many worlds don't accept the subjective leap it demands. However, studying quantum immortality is still interesting because it reveals something in us. I'm sure you experienced it while watching this video. It's our desperation to imagine consciousness as something more durable than our flesh. Our instinct to treat the self as fundamental even when neuroscience can't prove it. Our refusal to accept that death may not be a puzzle with a hidden loophole, but simply a boundary built into the kind of beings we are. And yet the idea doesn't disappear when the criticisms arrive. It survives for the same reason all powerful ideas survive. Because even if the theory fails as a science, it forces us to ask what we mean by self, what we mean by survival, what kind of continuity would actually satisfy us, and whether consciousness is a thing that can be counted the way we count particles and branches and probabilities. The concept is probably too unstable to believe, but it's almost impossible to hear it honestly and remain unchanged. Because once you've followed it to the end, even if you reject it, one realization becomes difficult to shake. The fear of death was never just about ending. It was about not knowing what exactly is ending when the light goes dark. By the end of all of this, quantum immortality begins to look less like a theory of eternal life and more like an instrument designed to expose the limits of human thought. It starts with physics, then slips into metaphysics, then into personal identity, and then into the biology of consciousness, and by the time you arrive at the true end, the original promise has almost entirely dissolved. It does not tell us, with any real confidence, that we survive death by riding the surviving branches of the multiverse. What it does tell us, much more clearly, is that our ordinary concepts of the self, death, continuity, and observation are far less stable than they appear. Quantum immortality is not powerful because it proves immortality. It is powerful because it weaponizes our uncertainty about what a person is. That's why the idea feels so hard to dismiss emotionally, even when it's weak scientifically. It attaches itself to something older than reason. The raw first-person fact that no matter how much you understand death in the abstract, you have never experienced your own absence. You have only ever experienced continuity. One moment leading into another, one conscious frame dissolving into the next. However rationally you accept mortality, experience itself keeps teaching the opposite lesson. You can imagine pain, you can imagine loss, you can imagine your funeral, your absence from other people's lives, your body decaying, your work unfinished, and your name fading. But all of that is still imagination happening from within our awareness. The one thing you cannot represent from the inside is the total disappearance of the representer, the end of the frame itself. And so the mind reaches for substitutions. Religion offers survival of the soul. Technology offers uploading the mind to some AI machinery. Legacy offers symbolic continuation, and quantum immortality offers branching persistence of consciousness. Different stories, all with the same end goal, trying to imagine a form of continuation because awareness cannot easily stare at a future in which it is not there to witness anything at all. But, if you ask me, I would say there's a hidden mercy in finitude. The old human dream was that death might not be final, but that finality might just be what gives life its meaning. Because endings do more than just stop things. They define things. A life is not meaningful merely because experiences happen within it. It's meaningful because it has boundaries, because choices exclude alternatives, because time runs one way. Love matters because people can be lost. Courage matters because risk is real. Urgency matters because there will not be endless chances to become who you want to be. Remove the reality of an ending, or even muddy it with endless branch-dependent continuation, and the structure of significance begins to distort. Life doesn't become infinitely precious. In fact, it's quite the opposite. And perhaps that is the final reversal. Quantum immortality begins as a rebellion against death, but it ends by making death look strangely necessary. Not desirable by any means, and not easy or fair, but necessary in the structural sense, as the horizon against which life becomes a whole rather than an indefinite residue. We started with hair. A single strand of human hair, 70,000 nanometers wide, and the incomprehensible fact that 700,000 protons can line up across it. We used that image as a measure of scale, a warning that we were about to go somewhere our intuitions were not equipped to follow. But here's what the image is also doing. Scale is not just a property of space, it's a property of understanding. There are things that are simply too large or too small or too strange to be held comfortably in a human mind. And for most of history, we've been okay with that. The quantum world was down there, somewhere else, and we were up here, and the gap between us was so enormous it insulated us. What this marathon has tried to show, across 6 videos, across entanglement and paradox and technology and consciousness and dreams, is that that insulation was never real. The quantum world isn't down there, it's not somewhere else, it comes to us, it comes up. It shapes how particles become atoms, how atoms become molecules, how molecules become the neurons that fire when you feel afraid, or curious, or certain of something that you can't prove. And if the last idea that we explored is correct, if the branching of the wave function means there is always a version of you that survives, then the quantum world doesn't just shape you. It won't let you end. You're not looking at the quantum world from the outside. You are an outcome of it. And what that means for your consciousness, for your survival, for every night you spend dissolving into sleep and waking up somehow still there, is the question that physics handed us, and it hasn't taken it back. Take a single strand of your hair and lay it flat on the table. Now look at it. At approximately 70,000 nanometers, this is one of the smallest things you can actually perceive with your own eyes. And even then, it's just barely visible on a good day. And if you're blonde, well, good luck. Now what if I told you that a single quantum particle, the proton, is about 700,000 times smaller than that